Yes, good morning, everybody. Can you listen to me? Please raise your hand. Yes, today will be one of the most important day for transients. And as I expect tomorrow, again, from 7 to 1, we will close the syllabus. And I'm sure by tomorrow, we can close the complete syllabus. Okay. Later, after some 10-15 days, I will put a doubt session. Again, some 4 hours doubt session. Anything extra you want to teach or extra you want or doubts, we will also plan that. Okay. That is my plan. Okay. But everything we are going to conclude by tomorrow. That is why we extended even one day. But today is the critical day for transients, and I want everyone to pay attention. I know afternoon class is not there. Yes. For you, evening class is not there. Yes or no? Please raise your hand. Evening class is not there. Yes or no? Yes. Happy Diwali to everyone. Okay. Everyone, happy Diwali. Bhavana, this anonymous attendee, Samruti Prasad, Imtiaz. Yes. Some students really keep asking good doubts. Pratibha, Ashish Raj, everyone plus everyone. Yes. There is no class. I don't tell lies. Anonymous attendee is giving me lies. There is no class. I inquired from Seshu. There is no class today in the evening. So Pakka, I will go up to 1. Everybody should cooperate, please. Today will be critical day for transients. Chalo. Now quick review what we did yesterday. Yes, everyone should pay some attention. What we did yesterday. Okay, when it comes to transients, I want everyone to pay some attention here. Yes, everybody. Now see this. What are transients? Transients are regarded as sudden change in the state of a network or circuit, which is indicated by switch operation or special functions. So that is why in this chapter, Nasar, switch is shown, like switch opening, closing. What they indicate? They indicate turning on, turning off process, adding a load, removing a load, open circuit, short circuit, all such sudden changes. So transients are regarded as sudden change in the state of a network or circuit indicated by switch operation or special functions. So that is why in this chapter, we can also show step input, ramp input, parabolic, etc. Impulse, sudden change. And basically, I categorize transients into 2 types. One is turning on process, that is called step response. Okay, turning on process, step response, where source is exciting the network. The other is called turning off process, source free response. Source is leaving the network. Okay, both are transients. Okay, both are considered as transients. Okay. Then why transients occur? Because nothing in the world can allow sudden change in 0 time. Allowing sudden change in 0 time is violation of law of conservation of energy. Energy can neither be created nor destroyed, but you can transfer from one form to another form, and hence transients will happen. Then in electric circuits, which elements are responsible for transients? Memory elements. That is, inductor will not allow sudden change in current, capacitor will not allow sudden change in voltage, but resistor can convert and dissipate energy. Hence, resistor will not create transient, but inductors and capacitors create transient. That is why you see the difference here in both the problems. I asked what is I of 0 plus. In resistor problem, I of 0 plus exists. That is, immediately they can convert and dissipate. That is also equal to I of infinity. But in an inductor problem, yes, inductor will not allow sudden change in current. So I of 0 minus 0. So I of 0 plus is also 0. However, final steady state value will be 10, but it will take some time to go. That is why transients, inductor will not allow sudden change, gradual change based on time constant we have to find. Then transients, though occur for short time, but they are deadly dangerous. Okay, and stability of the network will be tested there. Okay, and also designer is more interested in transient state behavior because that is where critical values in designs will come out. Okay, always dangerous is transient state. Then what are state variables? These are the critical parameters that should be observed. Okay, these are the critical parameters that should be observed. Okay, in a network, which can determine the correct state of a network. Okay, which can determine the correct state of a network. Okay, they are called what? State variables. Okay, in fact, they are called state variables. Okay, in fact, they are called state variables. Okay, now in a capacitor, voltage across capacitor is correct state variable, and inductor, current through inductor is the correct state variable. Okay, current through inductor is the correct state variable. Then in any circuit, there are 2 types of network, 2 types of responses. One is with source called forced response, which leads to steady state response. Okay, that is what we did NASA DC and AC steady state. Okay, this response is independent to the nature of passive elements, but purely depends upon the type of input. And also this can be different for different types of inputs. Like same circuit, you give DC, it behave differently, AC it will behave differently. Okay, and the solution for this part of differential equation is obtained by solving the particular integral part. Okay, particular integral. Then another response without source is called natural response, which leads to transient. How can circuits work without source? Because they have their initial conditions. Okay, memory elements, but this response is independent to the type of input, but purely depends upon the nature of passive elements. Okay. And it is unique, always unique. Okay. Like the natural responses of any circuit. And in differential equation, that is called complementary function part. So circuits and networks can respond even without source, provided they have some initial stored energy. In capacitor, initial stored energy, electrostatic energy give initial voltage. In inductor, electromagnetic energy give initial current. So conclusion is total response is force plus natural. This part we did, sir. Forced response we did. DC steady state, AC steady state, that we did. That leads to steady state, that is called zero state, particular integral. But this part we missed out. Natural response, which leads to transient, that is called zero input response, complementary function. That is why in this chapter, the missing part, see this right side missing part, we are going to find out first. Okay. This right side missing part, we are going to find out. Steady state, if it is DC steady state, DC voltage. If it is AC steady state, like AC current. But this missing part is there, the transient. Again, first order, second order, in second order, underdamped, overdamped, like that we are going to learn. Then order of a circuit or network, number of energy storage elements available in distributed form but interactive. Okay. Then yes, initial conditions. Okay, they come from the previous steady state. Okay. Then this is an important statement I told. Yes, analyzing circuits for sudden changes in time is transients. Then analyzing for S tends to infinity is also transients, because time and frequency are inversely proportional. T tends to 0 means S tends to infinity. Okay. Yes. That is why Laplace transforms are powerful tools in analyzing circuits during transients. Okay. And this is an important table coming from mathematics. That is very important table. Now in this chapter, we are representing our elements for any signal at any frequency. That is the meaning. We are representing our elements RLC for any signal at any frequency. Okay. However, resistor is independent of frequency. Inductor for any signal at any frequency is SL ohms. Capacitor for any signal at any frequency is 1 by SC ohms. Now, from that only, we can even conclude DC steady state, AC steady state, and now this special state called transient state, transit state, sudden change, 0 plus means S tends to infinity. Okay. That is a secret, sir. That is a secret, very important secret. Okay. Now, yes. Now let us continue further. Okay. Now I will categorize this chapter. Yes, everybody, I will categorize this chapter into, okay, 7 categories, sir. 7 categories. Okay. So first we are starting category 1. Everybody, first we are starting category 1. Okay. This is category 1. Category 1, which is called source free first order circuits. This is the first level we are going to start. Everything will be very important, sir. And by afternoon, we see how much content we can learn. What is the meaning of source free first order? Source free means turning on or turning off process. Source free means it is turning off process. Source free means source left, na? It is turning off process. And first order means only one energy storage elements. Chalo, in that, first RC circuit. Listen to the mathematics, sir. Everything comes from max RC circuit. So RC circuit I can take. Okay, RC. Now, what is the correct state variable to observe? Here, voltage across capacitor will give the secret. Voltage across capacitor is correct state variable. Okay, na? And moreover, how can this circuit work without source, provided there is some initial stored energy? So let V of 0 is some V naught. Then only it can work, na, sir. So first of all, there is no source. That means source initially charged the capacitor and it left. Okay, that is why it's called source free first order, because only one energy storage element, and state variable is what? Voltage across capacitor. Okay, state variable is voltage across capacitor. And how can this circuit work without any source? This circuit can work without any source, provided there is some initial stored energy. That let V of 0 is V naught. Okay, let V of 0 is how much? V naught. Okay, with that only it can work. V of 0 is V naught. Okay, V of 0 is V naught. So now, to get the solution, now when RC circuit is there, we should write KVL, KCL, KCL. Yesterday I told us, sir, state variable definition. You see now. See, yesterday we told an important definition called state variable. Okay. Yes, you see the meaning of state variable. I will give you here. State variable. These are the critical parameters. So in an RC circuit, what is the state variable? Voltage across capacitor. So what we should write? KCL or nodal equation. Yes or no, sir? See here. KCL or nodal equations we have to write. Okay. So I am coming there to write the KCL or nodal equation. Chalo, I am writing the KCL or nodal equation. So if I take this as reference, and this itself is node voltage V, which is my state variable. So if I write this current IC, this current IR equal to 0. My notation is nodal analysis. I assume all currents leaving the node as positive. So if I write that, okay, plus IC plus IR is 0. IC is C dV by dt. IR is V by R. V by R equal to 0. Okay. IC is C dV by dt plus IR is V by R equal to 0. So this is the first order differential equation governing the system. This is the first order differential equation governing the system. Okay, now please understand, this is the first order differential equation governing the system. Okay, now if you try to solve it, this C dV by dt is minus V by R, dV by V is minus dt by RC. So if I integrate, yes, if I integrate, okay, if I integrate, yes, please understand. So I can say this is natural logarithm of V is equal to minus T by RC plus integral constant. So this is V by A is equal to minus T by RC. So V is A e power minus T by RC. Now A is missing. Now we should observe initial condition. However, we know at T equal to 0, we already know at T equal to 0, capacitor was charged to V naught, then V equal to V naught. Now substitute here. At T equal to 0, V equal to V naught. So V becomes V naught into A. At T equal to 0, this becomes 1, this becomes 1. So automatically A is equal to V naught. So finally, this V of T is equal to, now A is nothing but V naught e power minus T by tau. That means RC for all T greater than or equal to 0. This is the answer. Or I can write the same expression as V of T is equal to V naught e power minus T by tau for T greater than or equal to 0. Here tau is nothing but RC, which is the time constant of the circuit. What is the time constant of RC circuit? Okay, na, time constant. So finally, you have to remember this equation, sir. Okay, okay, this equation or this equation, both mean same. Okay, that is the equation you have to remember. So mathematics is telling how this is working. Now, if you plot the function to understand, chalo, voltage versus time. If you plot, yes, voltage versus time, V of T versus T. So at T equal to 0, at T equal to 0, yes, put T equal to 0 here, e power 0, 1, that is V naught. It is at V naught. Okay. At T tends to infinity, e power minus infinity, it becomes 0. That means it is naturally decaying to 0 with a time constant, exponential decay function. That is mathematics is telling the story. Okay. That means, however, this is the initial value. Okay. Initial value. Okay. And here in this case, final value is 0. Final value is 0 here. Because this is turn off process, na sir, turn off process, final value is 0. Okay, now let us understand what does it means. Now, if I expand the expression, V at T equal to 0 is V naught. Okay, then V at T equal to tau. V at T equal to tau becomes how much? E power minus tau by tau, that is e power minus 1 into V naught. That is e power minus 1 into V naught. That is 0.367 V naught, e power minus 1, sir. Then V at T equal to 2 tau. 2 tau, e power minus 2 V naught. Okay, 0.135 V naught. V at T equal to 3 tau, e power minus 3 V naught. Okay, 0.049 V naught. V at T equal to 4 tau, e power minus 4 V naught. 0.018 V naught. V at T equal to 5 tau, e power minus 5 V naught. 0.006 V naught. Okay, that is the meaning there. That is the meaning. So now if you observe, yes, that means the system would have reached a final value almost 0 in 5 time constant. But in 4 time constant, it is almost reaching final value with less than 2% error. So that is why 0 to 4 time constants, okay, this 0 to 4 time constants is called transient state. 0 to 4 time constant is called what? Transient period. Transient period. Okay, it is called transient period. And for any time greater than or equal to 5 tau, for any time greater than or equal to 5 tau is called a steady state. Okay, for any time greater than or equal to 5 tau, okay, for any time greater than or equal to 5 tau is called steady state. Is called steady state. Okay, that is the meaning here. Please understand, everybody, please understand the meaning here. Okay, so please understand the meaning. So V of T until 4 tau almost reach final value with less than 2% error in the first 4 time constants. Okay. The response will almost reach final value with less than 2% error in the first 4 time constants. Okay. However, by 5th time constant, it is almost final value 0. Yes or no? That is why first 4 time constants are called transient period, and greater than or equal to 5 time constant is almost steady state. Okay. Now, if I throw tangent here, yes, you see at this point, see in the graph, if I throw tangent here at that starting point, yes, it will hit the first time constant. Now at the first time constant, if I project, at the first time constant, if I project this value, okay, let me write neatly. See here, I'm projecting a tangent here. Now, if I take this value here and here, this should be actually S 0.367 V naught. And if I project the second tangent here, yes, second tangent here, it becomes 2 tau. This becomes 2 tau. This becomes 2 tau. This becomes tau. And here, if I project, and observe here, this will be 0.135 V naught. Like that, it goes to 5 time constants is almost 0. Okay. 5 time constant is almost 0. Okay. That is the meaning there. Okay. So all this is coming from mathematics. Everyone should understand all this is coming from mathematics. Okay. Now, so this is the expression for this. Now, what is the definition for time constant? So now we understood now, sir. Time constant is the time taken by the response to reach. Time constant is the time taken by the response to reach 36.7% of its initial value while discharge. Yes or no? So now I can write the definition here. Time constant. Okay. It is the time taken by the response, yes, time taken by the response to reach 36.7% of its initial value, okay, of its initial value while discharging. Okay, it is a time taken by the response to reach 36.7% of its initial value while discharge. It is the time taken by the response to reach 36.7% of its initial value while discharge. Okay, or the second definition is more important. Okay, it is the time taken. It is the time taken by the response to reach, okay, to reach 63.2% to its final value, which I'll explain. Everyone go through this. Okay, see here now time constant. See from here I can say it is a time taken by the response to reach 36.7% of its initial value while discharging. Or I can also say it has reached this much to final value. See this much of initial value. See 0.367 of initial value or 63.2% to its final value. Either way we can tell, sir. It is a time taken to reach 36.7% of its initial value while discharging, or it is a time taken to reach 63.2% to its final value. Okay, 63.2% to its final value. So second definition is very famous, sir. Remember, second definition is very famous. Now, once you got the state variable, which is capacitor voltage, now remaining things we can find. Okay, what are the remaining things? First, capacitor current. IC is C dV by dt. Okay, C d by dt of V. But what is V? We got what is V? We got V naught e power minus t by 2. Now, V naught e power minus t by 2. Now, if I differentiate C V naught e power minus t by 2 into minus 1 by 2. Again, tau is RC na. So that is minus V naught by R e power minus t by 2. Okay, tau is RC na. Yes, minus V naught by R e power minus t by 2. Now, why minus came? See, why minus came? Simple meaning. See, here in my circuit, I took my own notation that all currents leaving positive. But after solving, we got, yes, IC negative. That means actual current is going now anti-clock. I took IC like this. Okay, but after solving IC negative means it is going anti-clock. That means capacitor is discharging energy to register the stored energy in capacitor, which is in electrostatic form. The stored energy in capacitor, which is in electrostatic form, is now given to register and dissipated in the form of heat. Okay, now the stored energy in the capacitor, which is in electrostatic form, is given to register, which is dissipated in the form of heat. Okay, which is dissipated in the form of heat. Okay, now that is the meaning there. That is the real meaning there. Okay, the stored energy in the capacitor is now dissipated in the register in the form of heat. That is the real meaning, sir. That is the real meaning of this. Okay, now yes, that is the real meaning of this. Okay, now yes, and then once you know the capacitor current, now I'm finding the power to register because state variable is voltage. That is V square by R. V square by R I will do. Okay, that is V naught square by R e power minus t by tau by 2. I will write tau by 2 watts. Why? Because actually voltage square I have to do. But V square become what? V naught square e power minus 2t by tau. I am writing t by tau by 2 watts. Then energy decay in the capacitor. Energy decay, that is half CV square. Half CV square. Now you may say, sir, how can you write directly? Because voltage state variable I know na. So energy decay in the capacitor is directly half CV square. Because energy stored in capacitor up to t is energy at t, we can find. So there is nothing but half CV naught square e power minus t by tau by 2 joules. Tau by 2 joules. Okay. Then once it is power energy, yes, when it is power energy, yes, when it is power energy, now charge expression also, Ohm's law, Q equal to CV, that is nothing but CV naught e power minus t by tau coulomb, t by 2 coulomb. Okay. Okay, now current through capacitor, yes, we got power in register, energy stored in capacitor, and charge. Okay, charge function in a capacitor. Okay, now all this we got. Okay. Yes, now once we got this, yes, now I'm going to RL circuit. Yes, B, RL circuit. So RC circuit I will review again. Everybody listen now. Those who joined late, slowly they are coming. See, sir, we started category 1. Category 1 is source-free first order circuits. Okay, it is turning off process of first order RC circuit and state variable is capacitor voltage. So I just wrote some differential equation. I got that. Don't worry about this. This is max only, sir. It is not a derivation. And after solving, I got this expression that capacitor voltage will decay exponentially with a time constant, where time constant is RC. This all came from mathematics only. And the expression I plotted, there is a green color function. Okay, then by 4 time constants, almost voltage has reached 0 with less than 2% error. Okay, less than 2% error. But in 5 time constant is almost reached 0. Okay, so first 4 time constant is called transient period and greater than or equal to 5 tau is called steady state. Okay, and based on that I got this. Okay, now based on that I got this. Okay, okay, now then here time constant definition I gave. Then after getting the voltage across capacitor, then current, power, energy, and charge. Okay, that square 2t by tau I am writing as t by tau by 2. That is why you see power function and energy function. Power in resistor and energy decay in capacitor is 2 times faster than voltage decay. Why 2 times faster? Because time constant has become half. Time constant become low means faster response. Time constant large means slow response. Okay. So now RL circuit. Everybody watch this RL circuit again. RL. Okay, RL. First of all, what is the correct state variable here? The correct state variable is current through inductor. Okay, correct state variable is current through inductor. Okay, now how can this circuit work without any source? This circuit can work without any source provided there is some initial conditions. So let I of 0 is I naught, then only it will work, sir. I of 0 is I naught, then only it will work. Otherwise, it cannot work. Okay, I of 0 is I naught. Okay, so now in that regard, everybody. Now here it is better to write KVL or KCL. KVL, inductor KVL, capacitor KCL. So if I write the KVL, I will take passive notation. This is plus VL and this is plus VR. This is plus VL and plus VR, and this is going clockwise KVL. Okay, KVL clockwise. Now if I go KVL, so here plus VL plus VR equal to 0. VL is LdI by dt. VR is IR equal to 0. VL is LdI by dt and VR is IR equal to 0. Now if I observe this LdI by dt is minus IR. So di by I, okay, this is di by I is equal to minus R by L into dt. Now if I integrate, okay, natural logarithm of I is minus R by L into T plus integral constant. So this is I by A is equal to minus R by L into T. So I is A e power minus R by L into T. R by L into T. Now, yes, at T equal to 0, we know already I is I naught. That is the initial condition. So if you substitute there, this I naught equal to A. So finally, we get this I of T. This current is a function. I of T is I naught e power minus T by L by R. I will write. See, this R by L into T, I will write T by L by R. So there is nothing but I of T is I naught e power minus T by tau. This is the expression. Okay. I naught e power minus T by tau, where tau is L by R, which is the time constant of the circuit. Okay, time constant of the circuit. Okay, this is for all t greater than or equal to 0. Okay, so that is the expression. Now here also if I plot again, yes, here also if I plot current versus time. Here state variable for RL circuit is current through inductor, sir. For RC circuit, state variable is voltage across capacitor, because that will tell the secrets in the circuit behavior. Now at t equal to 0, it is I naught, and t tends to infinity, it becomes 0 naturally as an exponential decay function. Okay, this is an exponential decay function. Okay. Now again, sir, here also if I throw tangent here, it will hit the first time constant, and at first time constant this will be like 0.367 I naught. So same explanation here also, time constant definition is same. Okay, so here also same meaning will come. Yes, it is a time taken, but only difference here, it is current. Okay, here we have to take what current we have to take. Okay, here we have to take their voltage, here current. Okay, current through inductor, same definition, same meaning of time constant. Okay, no need to repeat anything. Again, first for time constant is called transient value. The final value will reach by 5 time constants. So same explanation. Okay, once we got this, yes, once we got this expression here, yes, now here I will write the remaining things. Okay, remaining things. See, once we got inductor current, now voltage across inductor, again from Ohm's law, it is L di by dt, d by dt of I naught e power minus t by tau. Okay, L I naught e power minus t by tau into minus 1 by tau. Okay, that implies VL of t is, okay, that tau is L by R. Okay, so there is minus I naught R into e power minus t by tau volts will come. Okay, again voltage came negative, minus I naught R. Now what does it mean? See, I took passive notation first. Okay, but after solving, VL came negative, means now this is plus, this is minus. That means current is going from the positive terminal of inductor. That means inductor is releasing energy. Inductor is releasing energy. I told this point now, sir. Generally, inductors and capacitors are globally passive, but during transients, when they release energy, are said to be active. So in this mode, in source-free case, the inductor is releasing energy to the resistor. Now it is acting like a source. That is why VL came negative. Yes, VL came negative. Okay, na? That is the meaning here. VL came negative. Okay, na? Chalo, once we got this, then again power expression in register. Because current is state variable, this is, I will write like I square R. Okay, na? That is I of t square into R. It is a function. That is I naught square R. E power minus 2t by tau, I will write t by tau by 2 watts. Like that I will write. Okay, tau by 2 watts I will write. Okay, na? Similarly, if I go with energy decay in inductor, it is half L I square. Half L I square. That is half L I naught square e power minus t by tau by 2 joules. Then if I observe, yes, then if I observe everybody, now flux linkage in inductor psi is Li. Okay, Li. That if I take, that is L I naught e power minus t by tau volt second. Okay, L I naught e power minus t by tau volt second. Okay, na? Volt second. Okay, that is the meaning. So all the things we got. Okay, chalo. So we got two important things, yes, for RL circuit and RC circuit. Now let us expand, sir. Now, what is it is an IS question. What is the unit of time constant tau? So what is your answer? Answer is seconds. Yes, it is the time taken by the response. So the unit of time constant is seconds. Now in terms of units only, I'm comparing units. The unit for time constant of voltage is the same unit for time constant of current, because both are seconds only, na? Time constant for voltage is the time taken for voltage to decay. Time constant for current is the time taken for current to decay. Both are in seconds only. That is RC unit is seconds is equal to L by R unit is also seconds. See, I'm never saying RC is L by R, sir. I am saying the unit of RC is unit of L by R. That is units I'm comparing. In terms of units only, the unit of RC is seconds, the unit of L by R is also second. Now from this, I will ask a question. Okay, the unit of, okay, L by RC is dash. Okay, again, the unit of, okay, L by R square is dash. Now I'm continuing that question. Okay, the unit of, okay, R square C is dash. The unit of RC by L is dash. Okay, then the unit of, okay, then the unit of root L by C is dash. Then the unit of, okay, L by R square C is dash. L by R square C is dash. Okay, L by R square C is dash. L by R square C is dash. Okay, so I'm asking such questions. See, now listen. See, I'm comparing only units here. What I'm comparing? I'm comparing only units. Okay, I'm comparing only units. Okay, the unit of time constant of voltage is the same unit of time constant of current. Now the unit of L by RC. See, what is the unit of L by RC? R only, na? Units are ohms. Then unit of L by R square. L by R square is C, na? C means farads. Unit of R square C. R square C is L, na? L is nothing but Henry. Unit of RC by L. RC by L is 1 by R. 1 by R means conductance, Siemens or mho. Unit of root L by C. This is very famous in power system. Characteristic impedance, na? Unit of root L by C is R only, again ohms. Then unit of R, L by R square C. This was asked in IS. L by R square C is 1. That means unitless. This is unitless. No unit for this. It is a constant. See, such bit schemes looks very confusing. Everybody, why I'm writing such questions? Because such bits looks very confusing, but they come from these basics. Okay, they come from these basics. Okay, so now I'm extending further. Now I'm asking a question. Determine the time constants. Yes, time constants of circuits below. See these questions are determine the time constants of circuits below. Okay, I'm asking you to find the time constant. So in that first question, pay some attention, learn, sir. I know afternoon there is no class for you. Today, hard work, even for me, there is no Diwali first syllabus. Already so many days. This is the 20th day I'm taking, but so much data after 2 years, almost 1.5 years, I'm teaching so much data for your batch. Okay, this is a big batch. So many students are there. So everything I'm teaching, sir, all the possible cases. You see how many worked out examples I would have done. You see, it will be more than 500. I challenge it. You accept that or not? You reply me here. Did I do so many problems or not? You tell me. Reduction techniques. You tell me yes or no. You sincerely tell me, sir. Okay, anyone reply? You tell me whether I did so many problems or not. Yes, thank you, sir. But take your time. See, it is not necessary that everyone is understanding, sir. I accept. Take time, sir. You take time, but go through my notes, sir. Everything you do 3 times. No need to do any material. I'm telling you. Okay, sir. This question is, okay, this is, let us say, some 20 volts. Okay, this is 3 kilo ohm. This is 6 kilo ohm. This is something like, okay, 10 microfarad. I want the time constant. Second question also I will give here. Okay, here I am taking something like this. T equal to 0. This is now 1 ohm, 2 ohm, 3 ohm, 4 ohm. This is 10 millihenry. Okay, chalo. For these two, I want the time constant. So everyone listen now. Okay, chalo sir, listen now. I want the time constant. See here, switch is getting closed. Means source is coming, turning on process. So yes, though we derived initially the definition of time constant for turning off process, but the meaning is same. It is a time taken. Okay, it is a time taken by the response. Here, what is the response? State variables. Always remember. We are finding time constant of the circuit means time constant of the state variables. See, time constant of circuits means time constant of state variables only. State variables. So what are the state variables? Memory elements, that is voltages across capacitors and current through inductors. So though we are all talking time constant of the circuit, but they're nothing but the time constant of the state variables. Okay, they are the time constant of state variables only. Okay, chalo. That means in the first problem, it is the voltage across capacitor time constant we are finding. In the second problem, we are finding current through inductor time constant only. Okay. In the first problem, voltage across capacitor time constant. In the second problem, it is the current through inductor time constant only we are finding. Okay, na? Chalo, everybody now in that regard. Yes, everybody in that regard. Now here switch is getting closed. Okay, when switch is getting closed, yes, capacitor is getting charged, but capacitor will not allow sudden change in energy. It will charge gradually based on the time constant. Now for any RC circuit, tau is RC only. Okay, na? Yes, for any RC circuit, tau is RC because this is first order circuits are only one capacitor. But if there are more resistors, it is a R equivalent seen by the capacitor. But if there are more capacitors, it is a C equivalent seen by the resistor, like the Thevenin's reduction. Okay, na? So now if you see, yes, now if you see this left side problem, I am writing here, left side problem. So what happens? Switch has closed, ideal voltage shorted, switch has closed. Okay, now capacitor point of view, if you see, yes, see this now. Capacitor point of view, if you see, this is now 3 kilo ohm. Okay, this is now 6 kilo ohm. Okay, now this is the R equivalent seen by the capacitor. This is the R equivalent seen by the capacitor. Switch has closed, ideal voltage shorted. So now what is the R equivalent? Next page I'm writing. Yes, you see here, R equivalent is, yes, R equivalent is what? 6K in parallel to 3K. 6K in parallel to 3K. It is 2 kilo ohm, 2 kilo ohm. Then tau finally is R equivalent into C. That is 2 kilo ohm into C. What is C gave? 10 micro. So overall it becomes 20 milliseconds. 20 milliseconds. So the time constant of this circuit while capacitor is charging, because here capacitor is getting charged as we are turning on process. So it is R equivalent seen by the capacitor, which is 2K into 10 micro. Yes, it is 20 milliseconds. It is 20 milliseconds. Okay, 20 milliseconds. And it will take 5 time constants to go there. Okay, it will take 5 time constants to go there. Okay, It will take how many time constants, sir? 5 time constants. So 100 milliseconds to go there, almost 100 milliseconds to go there. Okay, that is the meaning. It will take 100 milliseconds to go there. Okay, na? That is the real meaning of the time constant. Okay, na? Suppose here switch was opening. Now everybody listen, sir. If switch was opening, this 3 kilo ohm become then this is turn off process. That is what we studied now. If switch was opening here, if switch was opening, then it is a turn off process. Then it is a discharging time constant. Then this 3 kilo ohm will not come into picture. Only this RC will come into picture. Then tau is RC. 10 micro into 6 kilo, that becomes 60 milliseconds. Okay, na? But here switch is closing means turn on process. That is why this is the time constant we got, which is 20 milliseconds. But if switch was opening, that is turn off time constant. Then this part only will work. This 3 kilo is open. So tau is RC. R is 6K. See, that is different. Okay. So see which is the process going on. Turning on or turning off, like that. So here also time constants are. Now for any RL circuit, time constant is L by R. But if there are more resistors, it is R equivalent seen by the L group. And if there are more inductors, it is a L equivalent seen by the R group. So here also switch has closed. Switch has closed, extra 4 ohms will come. Initially, when switch was open, 4 ohms was not there in the circuit. The moment I close, extra 4 ohms will come. Chalo, but here, however, ideal current source open. Okay, ideal current source open. This 4 ohms came. Okay, and this is the R equivalent seen by the inductors are. Okay, please observe. Current source is open. This is 1 ohm. This is 2 ohm. This is 3 ohm. And this is 4 ohm. Okay, now what I want the R equivalent seen by the inductor. This 1 ohm is not working now, redundant. So if you see R equivalent, what is R equivalent? 4 plus 2, 6 in parallel to 3. So here R equivalent is 6 in parallel to 3. That is also 2 ohm. Then tau is L by R equivalent. So L is how much he gave? L is how much he gave? 10 milli. 10 milli by 2. Answer is 5 milliseconds. So here time constant for the current through inductor is 5 milliseconds. Okay, time constant for current through inductor is how much? 5 milliseconds. And it will take 5 time constants, 25 milliseconds to go there. Okay, final value. That is the meaning. That final value will be DC steady state value. And we know inductors act like short circuit. That concept we know. DC steady state values we already know because DC circuit analysis we completed. But this part we missed out, transient part, that we are learning now. Okay. Now I am giving very good questions. Yes, now I am giving good questions now. Yes. I want the time constant of the circuit. U of t volt, 3 kilo ohm, 6 kilo ohm, 2 kilo ohm. Okay. 1 microfarad, 2 microfarad, 6 microfarad. Another question. This is some I u of t, means I gave some step current. Switch is closing here at t equal to 0. R, 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 L, L. Chalo, everybody see this now again. I am finding time constant. Everybody see this again. Yes, everybody see. Now I want the time constants of this circuit. See, I told you, sir, if there are more resistors, it is a R equivalent seen by the capacitor group, and if there are more capacitors, it is a C equivalent seen by the resistor group. As long as we can lump these capacitors into single element, it is only first order. So if I look from here, this is the point of separation. Here C equivalent will come. What is the C equivalent? See, 1 plus 2 parallel, na? 3 micro is in series to 6 micro. That becomes 2 microfarad, 2 micro. Then what is the R equivalent in here? Chalo, what is the R equivalent? Ideal voltage short. See, I know this is a step input. 10 U of t is a step input. That is why transient will occur. 10 U of t is a step input voltage. That is why transient will occur. But voltage source, you short it. Then 6K in parallel to 3K, 2K, 2K, 2K in series to 4 kilo ohm. So now tau is R equivalent into C equivalent. So that is nothing but 4 kilo into 2 micro. That is 8 milliseconds. 8 milliseconds. Okay, 8 milliseconds. So yes, that becomes how much? 8 milliseconds. So in 5 time constants, 40 milliseconds. Okay, in 5 time constant becomes 40 milliseconds. Okay, in 5 time constant become 40 milliseconds. Then here if you see switch has closed. Yes, here if you see switch has closed. Okay, then ideal current source open. Now if you see this separation, point of separation, this L equivalent is, see, once this current source is open, these two become series. That is very important. Current source open, L plus L, this becomes 2L. And if I go to R equivalent, this current source is open, switch has closed. Now R in parallel to 2R, R in parallel to 2R. Okay, that becomes 2 by 3R, 2 by 3R. Now tau is L equivalent by R equivalent. Okay, L equivalent by R equivalent. Okay, I'm repeating, sir. R equivalent seen by the inductor is R in parallel to 2R. That is nothing but 2 by 3R. So this becomes 2L by 2 by 3R. It is, yeah, 3L by R seconds. 3L by R seconds. Okay, it becomes 3L by R seconds. Yes or no? Yes, that becomes 3L by R seconds. Okay, that becomes what? 3L by R seconds. Okay, that is the meaning there. 3L by R seconds. Okay, now I am giving the gate question. Chalo everybody, this gate question. What is the time constant of the circuit? Okay, what is the time constant of the circuit? Your switch is closing at t equal to 0. This is 6 kilo ohm, 3 kilo ohm, 2 kilo ohm, and this is 10 microfarad. And this is a general question, dual to it. I'm giving a question which is dual to it, dual question. Some 2 amperes, 6 kilo ohm, 3 kilo ohm, 2 kilo ohm, and this is some 33 Henry I am taking. Switch is opening. Chalo sir, time constant of both. Chalo 1 minute time constant of the circuits I want. Yes, I'm giving the solution. Now everybody should listen now. See, here switch is getting closed. Okay, switch is getting closed and ideal voltage source is shorted. So now the R equivalent, see the R equivalent seen by the capacitor, we have to find. This switch is closed here in this case. And this resistor is 3 kilo. And this resistor is 6 kilo. 6 kilo ohm, 3 kilo ohm, 2 kilo. Okay, and we are finding the R equivalent seen by the, yes, R equivalent seen by the capacitors. Ideal voltage short, na? That is how. Switch has closed, ideal voltage short. So if you observe, now this is one single node. Everybody observe, this is one single node. And this entire thing is also single node. Yeah, this is one single node and this is one single node. So if you look from here, 6K, 3K and 2K are parallel. Yes, please observe here. Yes, if you observe, I can say here R equivalent is 6K in parallel to 2K in parallel to 3K. That is 1 kilo ohm only, 1 kilo ohm only. Then tau is R equivalent into C. Okay, 1 kilo into C. C is how much? 10 micro. So time constant is 10 milliseconds. See, sir, it was a gate question. Time constant is 10 milliseconds. So it will take 5 time constants, almost 50 seconds to 50 milliseconds to almost fully charge the capacitor. Now this is a ulta bit, sir. Here, dual. Here first current source and switch is opening. Here if you take current source and switch opening, here also first current source, open it. And switch opened. Now this is a circuit after the transit. This is a circuit after the transit. Okay. Here current source open, switch is opening. This becomes 33 Henry. This becomes 3 kilo ohm. This becomes 6 kilo ohm. And this becomes 2 kilo. Now it is a series RL. It becomes series RL. So tau is L by R. That is L is 33 Henry. R becomes all these three in series. 6K, 3K and 2K. 11 kilo. So tau is 3 milliseconds. Tau is 3 milliseconds. Okay. Tau becomes what? 3 milliseconds. That is the case. Okay, na? That is the reason. Okay, na? So like that. Now I am giving IES objective. Again, I am giving IES objective. What is the time constant of the circuit? $60 microfarad. Switch is closing at T equal to 2. Chalo, IES objective. What is the time constant of the circuit? Everybody 1 minute. What is the time constant of the circuit? Yes, I'm going with the solution, everybody. Here I'm asking, yes, what is the time constant of the circuit? Okay, everybody should answer this question. Okay, chalo, what is the time constant of the circuit? Now your switch is getting closed and there is an ideal voltage source. So if you observe, see after the change, what is happening? See after the change, this is 3 kilo, switch has closed and ideal voltage source, I will short it. Okay, ideal voltage source, I will short it. Now I need the R equivalent seen by the capacitor. Ideal voltage source, short it. 3 kilo, 3 kilo, 1 kilo. So I'm looking at R equivalent seen by the capacitor. Okay, it is a R equivalent seen by the capacitor. Okay, switch has closed. Ideal voltage source, looking from here. Okay, chalo, now if you look from here, I need R equivalent. Now this 3 resistors, 3 kilo, 3 kilo, 3 kilo is delta connected. Na? Yes, this is delta connected, sir. So I will convert this into star. I will convert this into star. This is important. This is the star point. Okay. These three resistors are delta connected. It is looking like this, but it is delta. I will convert into star. 3 kilo, 3 kilo, 3 kilo in delta. In star become 1 kilo ohm, 1 kilo ohm, and 1 kilo. Then what happens here? Then what happens? Yes, then what happens? See, then I can say this R equivalent is, now after removing the 3 kilo, this 1 kilo plus 1 kilo ohm plus this 1 plus 2. 2 kilo is in parallel to 1 kilo. So this become 1 plus 2 by 3 kilo ohms. This is 5 by 3 kilo ohms. 5 by 3 kilo ohms. Okay. This is R equivalent. Then what is tau? Tau is R equivalent into C. That is 5 by 3 kilo into C. What is C? C is 60 micro. 60 micro. Okay. This becomes 20. Okay. 20 now. 20. 25 is 100 milliseconds. So 100 milliseconds. So after 5 time constant, that is half second, it will become almost completely charged. That is the meaning there. Okay. Because kilo, micro, milli, and 25 is 100. 100 milliseconds is the time constant. Okay. So I'm asking a general question. This is a concept question. Concept. What is the time constant of the circuit? $20 U of t volts, 1 ohm, 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 5 millihenry, 10 millihenry. Okay. Chalo, what is the time constant? Now see, sir, in this problem, you cannot lump the inductors together. This is second order circuit. See, in all the previous problems, okay, you see now in some problems, if there are like here 3 capacitors are there, but you can lump here 2 inductors are there, you can lump into single element. So this becomes first order only. But here what happens, sir? Though there are 2 inductors, can we lump them together? No, this is second order. So here, okay, the 2 inductors, now listen, the 2 inductors cannot be lumped together. Okay, na? So it is a second order circuit. So it is a second order circuit, second order circuits. Okay, second order circuit. So it will have 2 different time constants. So this circuit will have 2 different time constants. Yes, this circuit will have 2 different time constants. Yes, this circuit will have what? 2 different time constants for 2 inductor state variable currents. For 2 inductor state variable currents. Okay, now the solution for these currents, the solution here can be easily determined by using Laplace transform, transforms. Listen this, sir. Okay. So that is very interesting. So here this circuit will have 2 different time constants for 2 inductor state variable currents. See, suppose I do mesh analysis like I1 of S. In Laplace, what I will do, I will convert everything into S domain. 20 by S, 111. This become SL ohms like that I will do. And I will take but suppose if this is I1, this is I2, this is I3, I1 and I3 are only called state variables. I2 is not state variable because inductor currents are state variables. So this first mesh current I1 and third mesh current I3 are the state variables. For this, they have 2 different time constants and 2 different segments of the circuit. So that is the meaning, sir. Here 2 inductors cannot be lumped. So it is a second order circuit. Moreover, it is not as pure series RLC or parallel RLC. If it is a pure series RLC or parallel RLC, which I told you canonical form, remember, sir, in resonance, I was teaching such things in phasor diagram also. If it is a pure series RLC or pure parallel RLC, they are called standard canonical form. Then there is an approximate time constant that I will tell you later. But this is double inductor problem, double inductor. So there are 2 time constants, and the solution to these currents can be determined easily by Laplace transform or simultaneous differential equation. I will also write or simultaneous differential equation. Simultaneous differential equation, which is very, very tough, sir, which is very tough. But Laplace is going to be easy. Such problems you can expect in IES conventional. Okay, such problems are there in IES conventional, but here there is a meaning. Everyone should understand that. Okay, na? So that is a concept that you have to learn. Yes, this circuit will have two different time constants. Yes, two different time constants in two different instances. Okay, that is what you have to understand. Okay, na? Chalo, sir. Now category 1 we are doing problems. Okay, I'm going to do the first problem. Okay, chalo. Now if V of 0 is 120 volts, find complete expression, okay, for Ix of t for all t greater than or equal to 0. Ix of t for all t greater than or equal to 0. And this is the circuit. .1 farad, 8 ohm, 12 ohm, 5 ohm, and this is current Ix. And this is V. Okay, look at the question, sir. If V of 0 is 120 volts, find the complete expression for current Ix of t for all t greater than 0. No. Today class has to go up to 1 o'clock. No way I'm going to stop by 10:30. Tomorrow I want to close everything, sir. Please. No one will request that, please. No one will request. Samruti Prasad, there is nothing, sir. Diwali, you can celebrate crackers, everything after 1, sir. Okay, in between break, we will take. No, sir, tomorrow I have to close because other batch is also pending. For me, offline is going on. It is also pending. They are already writing letter that SAR is going slow. But I'm teaching everything for a hardly 2 or 3 batches this time, sir. So even they, see, even offline is there, I will tell you the story. For you, afternoon class is not there. But for me, 2 to 5 offline class is there. 2 to 5 offline class is there. Please understand. Now, everybody, if V of 0 is 120 volts, find the complete expression for current Ix of t for all t greater than or equal to 0. Okay, na? Yes, if V of 0 is 120 volts, complete expression. Now, listen, sir. First of all, this is transient or not? Yes. Why? Why it is a transient? Because any response without source is a natural response, and natural response leads to transient. Okay, so first you should understand what question it is. There is no source. Without source also circuit can work because initial condition is given. And moreover is asking complete expression for current. So solution is asking, not the value. So first of all, this is a response without source. That is called source-free response. Okay, any response without source is called source-free response, and that leads to transients. Okay, na? Any response without source is called source-free response, and that leads to transients. Okay, now please understand that any response without source is called source-free response, and that leads to transients. And that leads to what? Transients. Please understand this. Okay, any response without source is called source-free response, and that leads to transients. Okay, na? And that leads to transient. Okay, na? And moreover is asking complete expression. So first of all, I say this is source-free. Yes, source-free means turning off process. First order, because only one capacitor na first order, and it is an RC circuit. So what is the state variable? Voltage only. So first find state variable. First always find state variable, whatever you may ask. This V of t is equal to V naught e power minus t by tau. We have derived, na sir. See, we have derived. Yes, everybody, we have derived that, na sir. See, for any source-free first order RC circuit, this is the expression, na? V naught e power minus t by tau. Yes, that is the expression we already know. Yes or no? That is the expression we already know. So this, yes, everybody please understand this. Yeah, V of t should be of this one. But V of 0, how much he gave? 120 volts. This is given. This is given. Now let us find the time constant. Tau is RC, na? R equivalent into C. Okay, if you observe now R equivalent, yes, if you observe the R equivalent, everybody, this is 5 ohms. From capacitor point of view, I'm finding this, everybody. What is R equivalent? Now this is 5 ohms, this is 8 ohms, this is 12 ohms. Now if you see the R equivalent, chalo, R equivalent is 5 in parallel to 20. That is nothing but, okay, 4 ohms. 4 ohms. That is nothing but 4 ohms. Now tau equal to R into C. What is that C? That C is 0.1. 0.1. Okay, that is 0.4 seconds. 0.4 seconds. Now I will say this V of t is V naught, okay, V naught, okay, that is 120 e power minus t by tau. So V of t is 120 e power minus 2.5 t for all t greater than or equal to 0 volts. Okay, we got this answer. But he's not asking V, na, he's asking what? We got the expression for voltage, but he's asking current, na, Ohm's law. See, once you know the voltage across capacitor expression, this branch 8 plus 12 is in parallel to this capacitor, na. This branch 8 plus 12 is in parallel to capacitor. So current will be V by R. R is how much? 8 plus 12, 20. So now finally Ix of t is this V of t expression, which is state variable, by 8 plus 12, 20. So Ix of t is, this is 120 by 20 e power minus 2.5 t. So final value is, that is 6 e power minus 2.5 t for all t greater than or equal to 0 in amperes. So if you just plot, just to understand, sir, just to understand, if I plot, okay, just to understand, if I plot, everybody, yes, current Ix versus t, if I plot, at t equal to 0, current was at 6 amperes. And as t tends to infinity, current decays to 0 naturally. Current decays to 0 naturally. Okay. Yes, at t equal to 0, current is at 6 amperes. But as t tends to infinity, current decays to 0 naturally. Current decays to 0 naturally. Okay. Current decays to 0 naturally. That is the meaning there. Okay. Na? That is a real meaning here. Okay. Na? So please observe that. Okay. That is very, very interesting here. Okay. So I'm going to the next question here, everybody. I'm going to the next question. Okay. This is a gate question given for ECE. Okay. Find I of t for all t greater than or equal to 0. Find I of t for all t greater than or equal to 0. Easy bits are category 1 easy bits. Your switch is opening. This is some 8 amperes, 1 ohm, 2 ohm, half Henry, and I'm asking this current I. Okay, everybody, please observe this question. Find current I of t for all t greater than 0. Find current I of t for all t greater than 0. Yes, find current I of t for all t greater than 0. Okay, chalo everybody. I'm giving you 1 minute. Try something. Find current expression I of t for all t greater than 0. Okay, now see here, I'm finding the expression for current I of t for all t greater than or equal to 0. Okay, now, so here switch is getting opened. See, the moment switch is getting opened, this current source is getting isolated from inductor, sir. Understand the meaning? Here the moment switch is getting opened, this 8 ampere and 1 ohm independent mesh, and this half Henry and 2 more are independent mesh. So they are separating. So inductor is getting turned off here. Yes or no? So I say the switch is opening. So switch open is inductor getting isolated. So it is source free in this case. Source free in this case. But don't always misunderstand switch opening means it is off only, and switch closing means on only. That you see the concept here. First of all, your switch opening will isolate the current source from inductor. So it is source free. Again, what is the order? Again, what is the order? First order. Why it is first order? Because only one energy storage element. And what is the correct state variable? Current through inductor only. Yes, current through inductor only is asking. So luckily here he is asking state variable. Now we know this expression for current is I naught e power minus t by tau. But here I naught is not given, sir. See, in the previous problem, he directly gave V naught. Okay, but here I naught he did not give. How to get I naught? Go to the previous steady state. So if I go to the previous steady state, t equal to 0 minus, t equal to 0 minus, please understand the switch was closed. Okay, at t equal to 0 minus, switch was closed. Switch was closed. And for DC, inductor acts like short. And for DC, inductor acts like short. Okay, this was previous steady state where initial condition come. I told you yesterday, na. See, previously when the switch was closed before 0, DC steady state it was. In DC steady state, inductor was short. And now this is I of 0 minus, which is our I naught. Now clearly you see, yes, this is shorted. This 1 ohm is also shorted. Okay, this 2 ohms is also shorted now. So full 8 amperes will go here. Yes, full 8 amperes of current will go here, and go here. Full 8 amperes of current will go here. So this I of 0 is 8 amperes. Okay. And then if I go to the next one, so we got I of 0. Now also we require what? Time constant. Also we require what? Time constant for t greater than 0. Now if you see the time constant, see after opening the switch, this part and this part became separate. See, this part is isolated from this part. Yes, after opening the switch, this is half Henry, this is 2 ohm, this is 1 ohm, and this is 8 amperes. 8 amperes. So after opening the switch, you see now. See, after opening the switch, they become independent mesh. So this is isolated. This is nothing to do with the circuit. Yes, sir. This is nothing to do. So here time constant tau is L by R. L by R. So L is 1 by 2 by R. It is 1 by 4th of a second. It is 1 by 4th of a second. Okay, now 1 by 4th of a second. Then I can say this I of t is, okay, I naught, okay, I naught, how much we got? 8 e power minus t by tau, t by tau. So final answer is, it is 8 e power minus 40 amperes for all t greater than or equal to 0. So if you plot current versus time, yes, if you plot current versus time, yes, this is 8 amperes and current naturally decays to 0. Current naturally decays to 0. Okay, this is 8 amperes and current naturally decays to 0. Okay, yes, 8 amperes and current naturally decays to 0. Think, sir, again think. This again is turn off process, because here switch opening will isolate. Yes, switch opening will isolate. Important, switch opening will isolate the inductor from the source. So this is again coming under turn off process. Okay, this is again coming under turn off process. Okay, once you understood this, chalo, I am going to the next model, everybody. Yes, this is a gate question, 2 marks. Okay, gate question, 2 marks. Determine energy stored in the capacitor, okay, determine the energy stored in the capacitor up to t equal to 2.5 seconds. Okay, determine the energy stored in the capacitor up to t equal to 2.5 seconds. Very interesting problem. Everybody should observe the circuit. The circuit has a lot of important details in it. $50 2 ohm, 1 ohm, 1 farad. This is 3 ohm. And your switch is getting closed at t equal to 2 seconds. T equal to 2 seconds. The switch is getting closed at t equal to 2 seconds. Please understand the concept. Switch is getting closed at t equal to 2 seconds. Okay. Determine the energy stored in the capacitor up to t equal to 2.5 seconds. Determine the energy stored in the capacitor up to t equal to 2.5 seconds. Okay, na? Chalo, I'm giving you 1 minute. Just think. I'm going to start solution, but think how to proceed. How to proceed, just think about it. Now I want everyone to listen, sir. Very interesting problem. See here, he is asking, determine the energy stored in the capacitor up to 2.5. Okay. Okay, well, later we will talk about energy, but first let us find the state variable. What is the state variable? Voltage across capacitor. And once we know the voltage across capacitor function, which is a state variable, yes, once we know the voltage across capacitor function, which is a state variable, then we can say energy stored in capacitor up to 2.5 is energy at 2.5. We learned such basics in chapter 4 now, sir. Energy stored in capacitor up to 2.5 seconds is energy at 2.5 seconds. Yes or no? Like that. But now, sir, again, everyone, here switch is closing. Here switch closing at t equal to 2 does not mean that it is turning on process. The moment you close the switch, everybody watch this. The moment you close the switch, this becomes short circuited, isolating the capacitor from source. Don't again misunderstand. Sir, here switch is closing, it is on process. No, 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 please. Switch closing is not on process here. Here switch is closing. Okay, then this source gets isolated from capacitor. So this is source free only, source free only. Again, what is the order? Only one capacitor. So first order only, first order only. And what is the state variable? State variable is always voltage across capacitor. So this I will find first. But because the switch is operated at t equal to 2 seconds, I will do in two parts. Part one. Okay, part one. First, I will start from 0. From 0 until 2 seconds. From 0 until 2 seconds, I will do. Why? See, the real transient happened here at 2 seconds, not 0, na, sir. See, in all the previous problems, the transient happened at 0. Yes or no? The transient happened at 0. But here the transient happened at 2, na. So I will do in two parts. First, 0 to 2 seconds. Now, 0 to 2 seconds is previous DC steady state. Previous DC steady state only. Chalo, for previous DC steady state, when switch was open, okay, capacitor access opens. Yes, switch was open, capacitor access opens. Okay, capacitor access opens. Okay, this become 50 volt. This become 50 volt. 2 ohm, 3 ohm, 1 ohm, and this become DC volt. Okay, now what is this DC volt? Total voltage into same by sum, which is 30 volts. Yes, this is DC 30 volts. That means until 2 seconds, that voltage is DC 30 volts. Now I'm going to part 2 solution. Chalo, part 2 solution. Okay, this is for all t greater than or equal to 2 seconds. Now this is where transient, source free transient. Why it is source free transient? See why? Because the moment I close the switch, 50 volts gets isolated from the capacitor because this is shorting this, na. This 50 and 2 ohms will work separately, but capacitor will not realize this voltage source as there is a short circuit here. Okay, so source free transient. Now here, this expression generally should be V of t equal to V naught e power minus t by tau. Now this is the expression we derived for t greater than or equal to 0. But now we should modify for t equal to 2. So now here V of 0 means V of 2 minus from previous state. Yes or no? From previous state. Here V of 0 means V of 2 minus from previous state. V of 2 minus from previous state. So what is V of 2 minus from previous state? V of 2 minus is only 30 volts. Okay. So V of 2 minus is 30 volts only. 30 volts only. Okay. 30 volts only. Then what is the tau? Tau for t greater than 2, I should go. So now t greater than 2, if I observe, this switch has closed. This 3 ohms is also shorted. Then only this part is working. Yes, why only this part? The moment I close the switch, this part is separate, sir. 50 and 2 ohms are nowhere connected to capacitor. And moreover, this 3 ohms is also shorted. So only 1 ohm and 1 farad will be there. Only 1 ohm and 1 farad will be there. So tau is RC. 1 second. So now I will write this V of t is V naught 30 e power minus t by tau. But t becomes t minus 2 by tau. Tau is 1. See why I wrote t as t minus 2? To show that this function is valid for all t greater than or equal to 2 seconds. See, in signals and systems, we learn, sir, everywhere. Okay, like what is the meaning? What is the meaning of u of t? U of t means it starts at 0. What is the meaning of u of t minus 2? It starts at 2. Like that. To understand, wherever t is there, put t minus 2. Here also, this is an exponential function. But to validate this expression from 2, To validate this expression from 2, wherever t is there, put t minus 2. So finally, I will write like this. Finally, the expression for voltage in 2 parts I wrote. First part is constant 30 volts, that is from 0 until 2 seconds. Second part is 30 e power minus t minus 2 by 1 second volts for all t greater than 2 seconds. Okay, greater than or equal to 2 seconds. Now, if I plot this just to understand, yes, everybody observe now, voltage versus time I am plotting, voltage versus time. So, voltage is constant 30 volts until 2 seconds. Chalo, voltage is constant 30 volts until 2 seconds. Until 2 seconds. Okay. Then later it started exponentially decaying. Yes, started exponentially decaying with a time constant of how much? 1 second. 1 second. That is the meaning. That is the meaning. So everybody observe now. See, once we got this, okay, let me complete this. Now, once we got this, now he's asking actual energy, but he's asking energy. Yes, he's asking energy. Now I can say energy stored in capacitor up to 2.5 seconds is energy at t equal to 2.5 seconds. Is energy at t equal to 2.5 seconds. There is nothing but half c v square, where v at t equal to 2.5 seconds. Where v at t equal to 2.5 seconds. Where v at t equal to 2.5 seconds. Okay, now v at t equal to 2.5 you substitute. Okay, v at t equal to 2.5 I substitute, that becomes 30 e power minus 2.5 minus 2 is minus half. Okay, 30 e power minus half you will get. Okay, you will get 30 e power minus half you will get. Okay, that I calculated, sir, already. Yes, it is there with me. And that 30 is 18.19. Now, this part you are getting how much is? Yes, this part you are getting something like 18.19 volts. 18.19 volts. Now, energy, yes, up to 2.5. Up to t equal to 2.5 is energy at 2.5. Half C is 1, V square, 18.19 square joules. Okay, that you will get something like 165.5 joules. Okay, that is a very interesting gate 2 marks, sir. Worth 2 marks. It is a worthy 2 marks question. It is a gate worthy 2 marks question. I will explain again. Everybody, look here. I am going to explain again. Everybody see here, sir. Here switch is closing, but that does not mean it is a turn on process. Though the switch is closing, the source is getting isolated from the capacitor. So this comes under source free only. But though is asked energy, but first let us find the state variable voltage across capacitor. Because once we know the state variable, energy stored in capacitor up to 2.5 is energy at 2.5, provided you know the voltage at 2.5 seconds. Chalo. So voltage we are finding. But because the change is happening at 2 seconds, I am doing like 2 parts. 0 to 2 is the previous steady state, and greater than 2 is the transient part. So previous state, that is 0 to 2, because switch is closing at 2. That means before 2, it was in the DC steady state. Capacitor is open. So that is 30 volts. At 2, the transient occurred. But the moment you close the switch, source is getting isolated. So it is source free response only. But this is the expression we derived for t equal to 0. But we need to modify for t equal to 2. That is v of 0 is v of 2 minus, and time constant also after 2. But wherever t is there, put t minus 2 as a mathematical expression to indicate that this solution is valid for t greater than or equal to 2. Now I write in two parts, and this is how I plot. Then energy stored in capacitor up to 2.5. Yes, energy stored in capacitor up to 2.5 is energy at 2.5. Yes, energy at 2.5, which is how much? Yes, which is 165.5 joules. Okay, which is 165.5 joules. Okay, that is the meaning there. That is the real meaning. Okay, now that is the real meaning. Now I'm giving another important question here. This is also gate question. If I of 0 is, yes, 12 amperes. Okay, if I of 0 is 12 amperes, determine, okay, determine complete expression for itself. Okay, complete expression for I of t for all t greater than or equal to 0. Okay. Half Henry. This is current I. 2 ohms, 4 ohms, plus and minus 3I. Okay, everybody observe, I am starting the solution now. Everybody observe the question, I am starting the solution now. Yes, everybody look at this problem, sir. I want everyone to cooperate here. Now see here, there is a dependent source. Dependent source cannot work on their own. There is no independent source. Please understand, this is a dependent source problem, sir. And there is no independent source. So this still comes under source free only. Source free. And what is the order? Only one inductor. So first order. And it is an RL circuit. So state variable is current through inductor only. Current through inductor only. Okay, na? Please understand, sir. This is source free only. So now directly we know this expression I of t should be of the form. Yes, I of t should be of the form. I naught e power minus t by tau. So I naught he gave, sir. Already how much he gave? 12 amperes. See the question. I of 0 is 12. This is already given. But the challenge is to find time constant. Time constant is L by R equivalent. Yes, time constant is L by R equivalent. So I want the R equivalent seen by the inductor while working. Look at this. So I want the R equivalent seen by the inductor while working. So if I look at the R equivalent seen by the inductor while working, see this circuit I will write first. I want the R equivalent seen by the inductor while working. This is 2 ohms, this is 4 ohms, this is the state variable current I, and this is 3I. But I want what? R equivalent. Yes, I want what? I want the R equivalent seen by the inductor while working. I want the R equivalent seen by the inductor while working. I want the R equivalent seen by the inductor while working. So no, yes, I want the R equivalent seen by the inductor while working. Please understand the meaning. Okay. So don't misunderstand, sir. So don't misunderstand. I opened it, the current is 0. No, not like that. I want the R equivalent seen by the inductor while working. Chalo, now this is clearly Thevenin's category 3. Only dependent source na, sir. Thevenin's category 3. Ohm's law. Chalo, let me inject a current of 1 ampere. It is easy to do and find V total across it. But this should be source notation because you are finding resistance by giving excitation, because this is pure category 3 where it won't work. So you have to make it work. So I'm giving a 1 ampere in the same direction so that substitution becomes easy. And I'll find V total like this because it is a source notation you have to take. Because category 3 we are giving energy na, sir, source notation. Source notation means current leaves positive. Chalo, I need this V total. So V total by 1 ampere is R. But I is 1. When I is 1, this becomes how much? When I is 1, this becomes how much? 3 volts. When I is 1, this becomes how much? 3 volts. Okay. When I is 1, this becomes 3 volts. Okay. This becomes 3 volts. I is 1, this becomes 3 volts. Okay. Now, chalo, now I need V total. For that, I will do nodal analysis. See now, let this be V total because this is positive na, V total. But this I will take it as ground. Negative na, this I will take it as ground. So if I write the nodal equation, everybody watch the nodal equation. Yes, from here minus 1 ampere plus this is V total by 2, V total by 2 plus this is V total plus 3 volts by 4. V total plus 3 volts by 4 ohm is 0. So minus 4 plus 2 V total plus V total plus 3 equal to 0. So from that I can write 3 V total is 1. V total is 1 by 3 volt. V total is 1 by 3 volt. Then R equivalent is V total by 1, that is 1 by 3 ohm. 1 by 3 ohm. Okay, then automatically, okay, tau is L by R. L is how much he gave? 1 by 2. By R is how much? 1 by 3. So it is 3 by 2 second. Now the expression for current I of t is I naught. I naught how much he gave? 12. I naught e power minus t by 2 minus 2 by 3 t for all t greater than or equal to 0. See how good this problem is, sir. How good this problem is. See, this is clearly source free first order only. Why it is source free? Because I told, sir, dependent source cannot work on its own. Please understand that. Yes, dependent source cannot work on its own. Please observe, everybody. Dependent source cannot work on its own. So there is no independent source. Without independent source means source free. So it is source free first order. And this is what we got. Okay, this is what we got. But determining time constant, that is R equivalent by using Thevenin's category 3. Why it is Thevenin's category 3? Problem with only dependent source. Na? Yes, then we got this R equivalent and then tau. Okay, now based on this another gate, similar question given was gate. Okay, find I of t for all t greater than or equal to 0. Okay, this was the question given. 100 volts, 2 ohm, 1 ohm, 3 ohm. Okay, find I of t for all t greater than 0. Find I of t for all t greater than or equal to 0. Okay, determine the complete expression for current I of t. Everybody should see now. Everybody listen again. See, this was a gate 2 marks, wonderful question. Now here switch is getting opened. When switch is getting opened, the independent voltage source is getting isolated from everything now, sir. When the switch is getting opened, the independent voltage source is getting isolated from everyone. So this is again source free because dependent source alone cannot work. So this is definitely source free. Okay, source free. Again, what is the order of the circuit? Only one energy storage in my first order. First order. And it is an RC circuit. So what is the correct state variable? State variable is voltage across capacitor only. State variable is voltage across capacitor. Once we get voltage, I is V by R. Okay, once we get I is V by R, that we can find easily. Okay, once we get that is I is V by R, that we can get easily. Okay, na? So now in that regard, yes, I can do like this. Yes, I can find this current after finding state variable. Now we know this expression for V of t is of the form V naught e power minus t by tau. Okay, but V naught he did not give. So go for t equal to 0 minus. If I go to the previous DC steady state, everybody watch this. Yes, this switch was closed, capacitor is open. So I'm writing the previous steady state circuit because it was in the previous steady state when switch was closed. Yes, when switch was closed, it was in the previous DC steady state. This is 2 ohm, this is 1 ohm, this is 3 ohm. Okay, this is I, and this is I by 2. This is I by 2, and this is 100 volt. This is 100 volt. Okay, so now in that regard, yes, now in that regard, I need this V of 0. Okay, this itself is V of 0. Okay, what I will do first, I will write a big mesh equation, then I will write a small KVL. So first I'm writing the big mesh equation. If I write the mesh equation, see out of I, everybody, out of I by 2 went. Out of I by 2 went. So this again becomes, this is open now, this again becomes I by 2. Okay, now KCL. See out of I by 2 went. So this is again I by 2. So minus 100 plus IR 2 into I by 2. Okay, plus this total is 4I equal to 0. So 5I equal to 100, I equal to 20. So I equal to 20. This is the first equation. Now if I write another KVL, if I write another KVL, minus 100 plus IR 2 into I by 2 plus V of 0 is 0. Okay, plus V of 0 is 0. So what we'll get then? Yes, what we will get then? That if you solve, V naught is 100 minus I into 1. So V naught is 100 minus I, we got how much? 20. 20 into 1 ohm, 20 volt. So this is 80 volt. So initial condition we got, sir. So everybody, this initial condition we got by going to the previous condition. KCL, KVLs are nothing to worry. DC basics, na? Yes, KCL, KVL, I got this. This is the second equation. Of course, that is the first equation. We solved, we got the answer. Now challenge is to find what? Challenge is to find what? Tau. Tau for t greater than or equal to 0, because we opened the switch at t equal to 0 now. Now I want the time constant, but what is the circuit after the change? Everyone observe here. The circuit after the change is something like this. Okay, now the circuit after the change is something like this. Okay, this is I, of course, this is I by 2. Okay, and this is 1 ohm and 3 ohm, and this is 1 by 32 farad. Because once the switch got opened, this 2 ohms is waste now. Once the switch got opened, 100 volts is left. 100 volts is left, and 2 ohms is also open waste. So this part only is there now. This part only is there. So I want the time constant. So I want the R equivalent seen by the capacitor. Yes. Now if you observe, yes, if you observe, this is the target terminals where I want the R equivalent seen by the capacitor. That is the concept here. So I want the R equivalent seen by the capacitor. Now this is Thevenin's category 1, 2, or 3. Thevenin's category 3. So here I will inject 1 volt. Yes, I will inject 1 volt and I will find I total. So 1 volt by I total is R. But the moment I inject 1 volt, this is 1 by 4, na? 1 by 4 amperes, because this is parallel. 1 plus 3 is in parallel. 4 is in parallel to 1 volt. So this is 1 by 4. Out of 1 by 4, half will go here. Out of 1 by 4, I by 2 means 1 by 8 will go here. So if 1 by 8 will go here, out of 1 by 4, 1 by 8. So this also become 1 by 8. KCL. See, sir, simple observation. I gave 1 volt and I need I total, sir. Thevenin's category 3. But the moment I give 1 volt, 1 by 4 amperes will go because they are parallel. Na? Now, if I is 1 by 4, this is I by 2. That is 1 by 8. So out of 1 by 4, if 1 by 8 go, another 1 by 8 should come here. So by observation, I total is clearly 1 by 8 amps. Then what is R equivalent? R equivalent is 1 volt by I total. That is 1 by 1 by 8. It is 8 ohms. Now, once we got this, now tau is R equivalent into C. R equivalent, how much we got? 8 ohms. C, how much he gave? Everybody watch this. C is 1 by 32 farad, sir. 1 by 32. 1 by 32 farad. So it is 1 by 4th of a second. Now I can say this V of t is V naught. See how much is V naught we calculated? Yes, V naught is 80. Okay, V naught is 80. V naught e power minus t by tau volts for all t greater than or equal to 0. So once we got V, but the original question is to find I na. Once we got V, what is I? Parallel. So I is V by R, but R is how much? 1 plus 3, 1 plus 3, 4. So now finally I of t is V of t by R. R is 1 plus 3, 4. That is 80 by 4 e power minus 4t. That is 20 e power minus 4t amperes for all t greater than or equal to 0. Outstanding question. Okay, na? Outstanding question. Okay, everybody. Understood, everyone? So take time, sir. Okay, take time. This is very, very interesting. I will give break. I will give break. Okay. Now this problem I'm giving and then break. This problem we will do after break, but I'm just giving the question here. Okay. Now everyone should think and answer this question. Yes, this question is given again in GATE 2 marks. Find A bit ratio of time constant of voltage by time constant of current. Ratio of time constant of voltage by time constant of current. B bit complete expression. Chalo, complete expression. Just complete expression for V of t and I of t for all t greater than or equal to 0. Okay, for all t greater than or equal to 0. Complete expression for V of t and I of t for all t greater than or equal to 0. This is something very interesting, special problem. I will continue after the break. But first observe, note down and try to do, sir. We'll continue this after the break. But this is now 20 u of minus t volts. Please understand, sir, everybody. This is 20 u of minus t. There is a concept here. 20 u of minus t volt. 20 u of minus t volt. This is 2 ohms, half Henry. This is 1 ohm, 1 farad. And here this is I and this is V. Chalo, find the ratio of time constant of voltage and time constant of current. Yes, find the ratio of time constant of voltage and time constant of current. Okay. Then determine the complete expression for V of t and I of t for all t greater than or equal to 0. Chalo, we'll continue after the break. So break will be half an hour. So come back by 9:45. 9:45, come back. Yes, everybody, welcome back. Are you there? Please raise your hand. Yes, sir. See, I want everyone to please cooperate, sir. I know it is a Diwali. Yes, I do. I do respect everyone, but please, sir, uh, please cooperate, sir. Today I need to stretch one maximum so that we are very comfortable tomorrow because I want to close the syllabus, sir. I actually promised the schedule manager that by Diwali I will close. But see, because here in online, everything question I am writing, answer I am writing, it is taking time, sir. It is taking time more than offline class. In offline, we used to dictate and we used to take material directly, but here it is not possible to synchronize everywhere. Chalo, everyone. Now see here, everyone. Yes. Now see this question, very interesting. Find the ratio of time constant of voltage to time constant of current. And moreover, I need the complete expression for voltage across capacitor and current through inductor. Now see these inputs are very, very special input here. See this input. What is the meaning of 20 u of minus t? See, sir. The meaning of 20 u of minus t means this voltage is defined in the negative time. This voltage is defined in the negative time. So it was 20 volts previously, suddenly becoming 0 at t equal to 0. It is 20 volts previously, but suddenly becoming 0 at t equal to 0. It is 20 volts previously, but suddenly becoming 0 at t equal to 0. Okay, that means it is turning off process. Yes, this is off. This is off process. That is very, very interesting. See, sir, that is off process. And voltage source becoming 0 can be replaced by short circuit. Short circuit, yes or no? See, here 20 u of minus t means voltage is suddenly becoming 0 at t equal to 0. Previously, it was 20 volts. So voltage source suddenly becoming 0 can be replaced by short circuit. Now tell me, this is first order or second order? Everyone will tell, sir, it is second order. But I say, no, they are two independent first orders. Why they are two independent first orders? Why? Because, see, this short circuit, because this voltage source suddenly becoming 0, this voltage source suddenly becoming 0 will make a short circuit. And the short circuit across this branches of RL and RC will not allow the inductor and capacitor to interact. So order of circuit represents number of energy storage elements available in distributed form, but interacting. But here, I know inductor and capacitor are separate, but are they interacting? They are not interacting here. See, I will tell you the meaning now. Everybody should watch this. I will tell you the meaning. Everybody, please watch this. What is the meaning of this? Let us understand. See, actually the short circuit which comes because of this voltage source becoming 0. Yes, the short circuit which is coming because of voltage source becoming 0 is not allowing the inductor and capacitor to, yes, it's not allowing the inductor and capacitor to interact. Okay, this short circuit across this is not allowing the inductor and capacitor to interact. So they become two independent first order circuit. This is also equivalent to something like this now. See, I can write the same thing like this. Okay, I'm writing like this. Okay, so this becomes 2 ohms, half Henry, and this becomes 1 ohm, 1 farad. And the short circuit, I wrote here as short circuit. Across, yes or no? That is the concept. So whatever energy in the inductor will be going through resistor, whatever energy in the capacitor will flow only through resistor. There is no potential difference for current to flow between the loops. So the short circuit is not allowing the two state variables to interact. So this is the current through inductor and this is the voltage across capacitor. They become two independent first order circuit. Independent first order RL circuit, independent first order RC circuit. So now the first bit. Now time constant for current is L by R. That is L by R. That is 1/4 of a second. Yes or no? Yes, 1/4 of a second. Then time constant of voltage RC. That is 1 into 1. That is 1 second. So the first bit, the ratio of time constant of voltage by time constant of current is 1/4. It is 4. First bit is 4. Now, second bit is asking complete expression. But because we know it is source free first order RL and RC, V of t will be of the form V naught e power minus t by tau of voltage, and I of t will be like I naught e power minus t by tau of current. Yes, one is time constant for voltage and one is time constant for current. Yes or no? Chalo, we require these two things. Yes, we require these two things. Okay, everybody? Yes, we require these two things. Now, in that regard, Chalo, first, how to get V naught and I naught, go to the previous steady state. Now, if I go to previous steady state, yes, if I go to the previous steady state, then this 20 volts DC source was there. Na? When I go to the previous steady state, this 20 volts DC source was there. So this becomes a DC steady state problem with 20 volts. 20 volts. Then for DC steady state, inductor short circuit, capacitor open circuit. Okay, inductor short circuit and capacitor open circuit. This is however 2 ohms, this is however 1 ohm. And this becomes I of 0 minus, and this becomes V of 0 minus. Okay, na? Yes. Chalo, now in that regard, if I observe these two, yes, if I observe these two, now what is this current voltage by resistance? 10 amperes. And this voltage is directly 10 to the 20 volt. Chalo, this itself is this. Now finally we get this V of t is equal to V naught is how much? 20 e power minus t by 2. But time constant for voltage is 1 second. So t by 1 second volts for all t greater than or equal to 0. And I of t is I naught. How much is I naught? We got 10 e power minus t by 2 minus t by 2. But what is tau for current? Tau for current is 1 by 4, 1 by 4. So t by 1 by 4 is 4t amperes for all t greater than or equal to 0. So these are the answers. Wonderful question, sir. See, everyone will feel initially there is a second order question. No. 20 u of minus t means 20 volts is suddenly becoming 0 at t equal to 0. Yes, 20 volts is suddenly becoming 0 at t equal to 0. That is the meaning here. So 20 volts suddenly becoming 0 at t equal to 0 is like voltage source becoming 0 is like short circuit. So when you short the system, these two LNC are not interacting. Order of circuit represents number of energy storage elements available in distributed form, but interacting. Are they interacting? Not interacting here. Yes. When they are not interacting, they become two independent first order circuits. Yes or no? They become two independent first order circuits. That is what you have to understand. They become two independent first order circuits. Yes, that is what it will come like this. Okay, that is the meaning here. That is the real meaning here that you have to understand. That is the real meaning. Everyone should understand. Okay, very, very interesting problem. So now I'm giving the gate question 2 marks. Recent 2019 questions are for electrical. If V of 0 is 4 volts, if V of 0 is 4 volts, determine the charge, determine the charge transferred by the capacitor determine the charge transferred by the capacitor from 25 microseconds to 100 microseconds, from 25 microseconds to 100 microseconds. Okay, if V of 0 is 4 volts, determine the charge transferred by the capacitor from 25 microseconds to 100 microseconds. Chalo, sir, everyone try. This is a gate question, 2 marks. If V of 0 is 4 volts, determine the charge transferred by the capacitor from 25 microseconds to 100 microseconds. Chalo, I'm giving you 1 minute. Try something immediately. Yes, everybody listen now. See, here switch is getting closed. I know, yes, here switch is getting closed, but that does not mean it is step response. Though the switch is getting closed, but that does not mean it is turn on process, because there is no source. There is no source, only the stored energy in the capacitor. Let me correct it. Only the stored energy of the capacitor is driving the circuit. So though the switch is getting closed, yes, please, here, though the switch is getting closed, this is not turn on process. This is still source free only. Yes, this is source free, because there is no independent source free. Again, what is the order? First order. What is the state variable? Because it is RC circuit, voltage is the state variable. Now this will be of the form, this V of t is equal to V naught e power minus t by tau. V of 0 is how much? 4 volts. V of 0 is 4 volts. Okay. Tau is how much? RC, 25 microseconds. Okay. So now this V of t is equal to V naught e power minus t by tau, 25 micro. Now charge function, because he's asking charge Q equal to CV. C is how much? Clearly 5 micro. 5 micro into 4, that becomes 20 micro. 20 e power minus t by 25 microcoulomb. Okay, because 5 micro into this, na sir, 20 micro. 20 I wrote here. Microcoulomb is the unit. Now charge transferred from 2.5 second, 25 micros to 200, na, there is difference. So first of all, charge at t equal to 25 microseconds is equal to 20 e power minus 1 microcoulomb. Okay, that is 7.35 microcoulomb you'll get. And charge transferred, yes, at t equal to 100 microcoulomb, 100 microseconds is 20 e power. Okay, see, this is 20 e power minus 1. Why? Because this is t is 25, but at 100 this become e power minus 4 microcoulomb. This will be 0.35 microcoulomb. So the charge transferred, so Q transferred is the difference now, sir. So Q transferred is the difference. That is Q at t equal to 25 microseconds minus Q at t equal to 100 microseconds. That is nothing but 7.35 minus 0.35 microcoulomb, which is 7 microcoulomb is the answer. Wonderful question, sir. Get 2 marks. Worth 2 marks gate question. Yes, it is a worth 2 marks gate question. Okay, everyone should understand that. Okay, it is a worth 2 marks gate question. Everyone should understand that. Yes, sir. Some students wrote, sir, 6.97. Wonderful, sir. 6.987. 100%. Very, very good, sir. Now the Bhavin, Imtiaz, fine. Bivalendra, fine. Okay, Yogesh, your answer. Check it. No problem, sir. Very good. Very good. Okay, so please observe, sir, this is not turn on process. This is still turn off only. Why? Because there is no source. Only stored energy in the capacitor is driving the circuit. So this becomes source free first order RC circuit only. Source free first order RC circuit only. Okay, that is the meaning there. That is the meaning. Okay, na? Chalo, now in that regard, yes, now we are going to category 2. So category 1 is over. That is source free first order over. Now we are going to step response of first order circuits. Step response of first order circuits. Yes, everybody should understand this. Okay, step response of first order circuits. Okay, step response, that means turning on process. In that, again, RC circuit. Okay, if I go with RC circuit, now here the concept is turning on process. So there is a source which is a DC voltage source. I will take it as Vs, and switch is getting closed at t equal to 0 is RC. So here again, what is the state variable? Voltage across capacitor only. Okay, voltage across capacitor only is the state variable. Okay, here again, voltage across capacitor is only the state variable. So now we know, because it is turning on step response, here total response is forced response, which is steady state response, plus natural response, which is transient response. See, in the previous category, why I did not write like this? Because in the previous category, the steady state is 0, because final value is 0, na, sir? See, what is the previous category? See, previous category, what we studied, everybody. See, previous category, what we studied, this RL and RC. This is turning off process. In turning off process, what is the final value? 0. That is why only transient part we wrote. Steady state part is 0, na? Because in the first category, source free first order, it is turning off process. In turning off, what is the final value? Final value is 0. Final value is 0. Yes, when final value is 0, that is why only transient part we wrote. But here you see this is turning on process. So final value steady state exists. That is given. Now this solution, sir, here also you can take differential equation. See what I can take. This I can take it as a reference. This itself is the node voltage. I can write KCL. This current plus this current is 0. If I write actually KCL, this current is C dV by dt. And this current is V minus Vs by R equal to 0. Now same, sir, if you differentiate, take initial condition, all this, sir, it will come. That part I can do, or you can do. This solution, directly I'm writing, this solution is of the form, this solution is of the form V of t is equal to V of infinity plus V of 0 minus V of infinity into e power minus t by tau. Okay, this solution is of the form, yes, this solution is of the form V of infinity is V of 0 minus V of infinity e power minus t by tau. Yes or no? Yes, V of infinity plus V of 0 minus V of infinity e power minus t by tau. Where what are these things? Where V of 0 means voltage across capacitor, before switch operation, in previous steady state, then V of infinity is what? Yes, voltage across capacitor, yes, voltage across capacitor after switch operation, yes, after switch operation in next steady state, and tau is RC, time constant. Okay, na? So here finally remember this equation, sir. This derivation don't need to worry. However, while doing problem, I will do that. Don't worry, sir. But remember this expression. So in step response, you have to remember this: V of infinity, V of 0 minus V of infinity e power minus t by 2. V of 0 means previous steady state voltage across capacitor. V of infinity means next steady state voltage across capacitor, and tau is RC. And what is tau? Tau is RC. Okay, tau is RC. Okay, that is what you have to understand. So now here case one with initial condition given, with initial condition existing. Okay, with initial condition existing. Yes, with initial condition. Now let V of 0 is V0. Let V of 0 is V0. Okay, let V of 0 is V0. But what is V of infinity here? For our problem, what is V of infinity? Let us assume already capacitor has initial condition V0 plus I am giving the source voltage. And what is V of infinity? And steady state V of infinity, capacitor acts as open circuit. In steady state V of infinity, capacitor acts as open circuit. Okay, then V of infinity is Vs only. V of infinity is Vs. So this expression will become V of infinity plus V of 0 minus V of infinity e power minus t by tau. E power minus t by tau. So if you plot it, yes, if I plot it carefully, if you plot voltage versus time, if I plot at t equal to 0, it was at V0. T tends to infinity, it reaches Vs. Okay, it starts at V0 but reaches Vs, but not suddenly, gradually with the time constant. That is the meaning. That is with initial condition. Now case 2, yes, case 2 without initial condition. Okay, now without initial condition, let V of 0 equal to 0 volts. Let V of 0 is 0 volts. Okay, and then there is no initial condition. However, V of infinity is again Vs only. Okay, then V of t becomes what? Because V of 0 is 0, that is Vs into 1 minus e power minus t by tau will come. Yes, V of s into 1 minus e power minus t by tau will come. Okay, for all t greater than or equal to 0. This is also for all t greater than or equal to 0 volts. Now here also, if I observe this, voltage versus time, if you observe, yes, it starts at 0, reaches Vs. It starts at 0, reaches Vs, but not suddenly, gradually with the time constant. Gradually with the time constant. Gradually with the time constant. Yes, it starts at 0, but reaches Vs. Yes, it starts at 0, but reaches Vs. Not suddenly, but gradually with the time constant. Okay, gradually with the time constant. Okay, that is the meaning there. Gradually with the time constant. Okay, now that is very, very important. So with initial condition, without initial condition, that is very important. Now finally, now once you get the state variable, that is capacitor voltage, now current. Now IC is C dV by dt, C d by dt of V of t. I will take the easy expression. See, one is with initial condition, one is without initial condition. Let me take the easy expression to understand the concept. Later in exam or whatever question, depending upon that, you can take anything, sir. But I will take the easy one. So I will take this expression, that is Vs into 1 minus e power minus t by tau. I will take. That becomes what then? That becomes CVS. Okay, I'm writing here. That becomes CVS. Okay, all mathematics, sir. See, first mathematics only will help us to understand. Now, first today I told electrical engineering, we are learning with max. So this is CVS. Differentiation of constant is 0. E power minus t by tau into minus 1 by 2. Tau is RC now. So this IC of t becomes what? Tau is RC. So this becomes Vs by R e power minus t by tau for all t greater than or 0. So if you observe here, now if you observe, so this becomes Vs by R and it naturally decays to 0. Naturally decays to 0. Naturally becomes 0. Okay, that is how. That is the meaning there. See, once I know these things, yes, once I know capacitor current and also capacitor voltage, okay, yellow capacitor current and capacitor voltage. Now I am going for power. Now power is voltage into current. Voltage into current. So this power will become what now? This is Vs by R into e power minus t by tau into this. That is nothing but Vs square by R into e power minus, yeah, if you observe e power minus t by tau minus e power minus 2t by tau watts. Then energy is what? Energy is integral power. Integral power. Energy is integral power. Okay, what is integral power? That is 0 to infinity. Okay, 0 to infinity. So that will become how much? Yes, half C Vs square joules. Why? Because we turned on the switch at 0, final value is infinity. So energy stored in capacitor up to infinity is energy at infinity. But what is the voltage at infinity? Vs only. So that is the meaning we got energy also. That is energy in the capacitor. Okay. Then register parameters also. Now IR. Now what is IR of t? Same, because they are in series, same expression. Current in capacitor is current in resistor. There is nothing but Vs by R into e power minus t by tau. Then what is voltage across resistor? I into R na? That is Vs into e power minus t by tau. Power. What is power? Voltage into current. That is Vs square by R into e power minus 2t by tau watt. This is in watts. This is in amperes. This is in volts. Then energy in resistor. Okay, energy in resistor is integral power dt, integral power dt, but long back to, so that will be, yes, that will be half CVS square joules only. Now, efficiency of RC circuit. This is very interesting, sir, which I will tell you. Output by input into 100%. That is nothing but output by output plus losses. I will explain, sir. Output plus losses into 100%. Now output is what we can recover, that is in the capacitor. But what is the energy stored in the capacitor? Half CVS square. Half CVS square. Here also output is half CVS square. But what are the losses? Energy dissipated by the resistor. See, losses are energy dissipated by the resistor, which is again half CVS square into 100%. So efficiency of RC circuit is only 50%. Go through all these things, sir. I will explain. Go through all these things. I will explain. Okay. Go through all these things. I will explain now. Yes, everybody really. I was again, sir, upset with stomach, sir. I had breakfast in the break, but then I was not comfortable. So please, sorry for wasting your time. Really sorry for wasting your time. But sir, listen, sir. Everyone, listen. See, we came to know second category, sir. What is the second category? Second category is turn on process of first order circuits. What is category one? Category one is turn off process of first order circuit. But second category is turn on process, step response. And this equation you have to remember. If it is an RC circuit, voltage is a state variable. You have to find initial value, final value, and also time constant. Now with initial condition, this is how it looks. Without initial condition, it starts from zero. Then expression for current. Once you get voltage and current, power, energy. Now you integrate this, you get or directly erode. Why? Because energy is stored in capacitor up to infinity is energy at infinity. Na? Energy is stored in capacitor up to infinity is energy at infinity. But what is the voltage at infinity? But what is the voltage at infinity? Vs only. Vs only. Okay, na? That is the meaning. Then again, current through resistor is same as current through capacitor, voltage, power, and energy. Okay, now what is the meaning of efficiency here? Now this bit was asked in gate 2 marks, sir. This bit was asked for electrical and also EC it was asked. What is the meaning of efficiency here? See, here once you turn on the circuit, initially capacitor keeps on charging until how long? Until V become Vs. Until V become Vs. Then current becomes zero. Until V become Vs and current becomes zero. So okay, so you see this now. What is the meaning? Initially capacitor keeps on charging until V become Vs. Then current becomes zero. V become Vs and current becomes zero. Now, what is the output energy? That energy which you can recollect. That is energy in the capacitor. What is the losses? That energy in the resistor is losses. So, see, the output energy, this is output. This is output. Where energy in the capacitor can be recovered. But this is losses. This is losses. That is dissipated by the resistor. So, efficiency is 50%. Okay, na? Now I'm asking a gate bit here. Now I'm asking this gate bit. Okay. In this. Okay, in this RC circuit. Okay. In the RC circuit above. Okay, in this RC circuit above. That means previous. The total energy supplied by the source is dash. The total energy supplied by the source is dash. Okay, the total energy supplied by the source is dash. You have to understand that. The total energy supplied by the source is dash. Okay. Now, if you observe the total energy supplied by the source, yes, the total energy supplied by the source, everybody. Now, you know, energy total supplied by the source is, that is energy stored in the capacitor plus energy losses. Energy stored in the capacitor plus energy lost or dissipated by the resistor. Okay, this is half CVS square until infinity. This is also half CVS square. Yes or no? Plus half CVS square. So total energy will be CVS square joules. That is very, very interesting. Now gate bit also I'm giving. Gate bit also I'm giving. Okay. Now this gate bit is, what is the total energy? Yes, what is the total energy? Okay, supplied by the source, in charging the capacitor completely. What is the total energy supplied by the source in charging the capacitor completely? Okay. So write the answer. What is the total energy supplied by the source in charging the capacitor completely? Yes, I'm going with the answer, everybody. Yes, everybody, let me see how many answered it. Very good, sir. I'm getting very good responses. Today is the hard work for us. The real Diwali is to really complete a lot of things, sir. It is a real hard work. See now, see here, everybody see here. See here, I know switch is getting closed. Here switch is getting closed. I know transient will occur, but all the basics we know, sir. If you do in a normal way, it will take hell of time. But with the concept, what I told here, total energy supplied by the source in charging capacity complete is CV square. So E total is CVS square. C is 2, Vs square, 10 square. So 200 joules. Simple, sir. Simple answer. But if you do in a normal style, okay, first finding voltage, then current, then power and energy, all this if you do here, you will get a hell of a time. It will take 10 minutes. But the student who know the basics, he will do in 1 minute. So that is the intention of asking this question. So now let us go to RL circuit. Chalo everybody, RL circuit. Okay, I'm going to RL circuit. So here I am taking step response of first order RL circuit. State variable is correct. Okay, here state variable is correct. Now again here total response is forced response which leads to steady state plus natural response which leads to transient. Okay, total response is forced response which leads to steady state and natural response which leads to transients. Okay, again if you write a KVL here, if you write a KVL, minus Vs plus IR plus L di by dt you will get. So from that I can write L di by dt plus IR equal to Vs. This is the first order differential equation. You can solve this, but I'm directly writing the derivation is very simple, sir. Similar way, but this solution is of the form. This solution is of the form. This solution is of the form. Okay, this I of t is equal to I of infinity plus I of 0 minus I of infinity into e power minus t by 2. Okay, this solution is of the form I of infinity is I of I of t is I of infinity plus I of 0 minus I of t e power minus t by 2. Okay, where again these things you should know. I of 0 is current through inductor before switch operation in previous steady state. Then I of infinity current through inductor after switch operation. Okay, after switch operation in next steady state. Then tau is L by R time constant of the RL circuit. Tau is L by R time constant of RL circuit. Now here also case 1 with initial condition given, condition given. Chalo, if initial condition given, let I of 0 is I naught. Okay, now let us assume already inductor having current. Now I am giving another source. Then what is I of infinity in this case? See, what is I of infinity? See, if I close the switch in DC steady state inductor short now, I of infinity is Vs by R only. That becomes Vs by R only. Okay, that becomes Vs by R. So now this I of t is I of infinity plus I of 0 minus I of infinity into e power minus t by tau. So if I observe now current versus time, yes, if I observe now current versus time, it starts at I naught, reaches Vs by R, but not suddenly, gradually with the time constant. Then here case 2 without initial condition. Without initial condition. Let I of 0 is 0. But what is I of infinity? I of infinity is Vs by R. Okay, I of infinity is Vs by R. Okay, then this I of t is I of infinity into 1 minus e power minus t by tau. This for all t greater than or equal to 0. This is for all t greater than or equal to 0. Then if I show this, yes, then if I show this, it starts at 0 and reaches final value, that is Vs by R. Okay, yes, it starts at 0, reaches final value. That is the difference. Previously it starts at I naught, reaches final value, but here it starts at 0. That is the only difference. Now once you got inductor current, now voltage across inductor from Ohm's law, V is L di by dt. But you can take any expression, sir, but I will take the easy one here. Later in exam or in question, if initial condition is also given, we will take this expression. Concept is same. So I will take the easy expression, right side expression I am taking, that is without initial condition. Vs by R into 1 minus e power minus t by tau. LVS by R, okay, into 0 minus e power minus t by tau into minus 1 by tau. Okay, so this VL of t is, okay, VL of t is tau is L by R na, so Vs into e power minus t by tau volts. Then once you get this voltage, yes, once you get this voltage, and also we got what current, then I'm going to power. Power in inductor is what? Power in inductor, voltage into current, voltage into current function. So that is again Vs square by R. You see here, this and this Vs square by R, e power minus t by tau minus e power minus 2t by tau. Watts. Then energy in inductor, integral power dt, 0 to infinity. Then directly I'm writing half L I square. Half L I square. Why I wrote like this? Because here we turned on the switch at 0. So it starts from 0, but final value means infinity. So energy stored up to infinity is energy at infinity. But what is the current at infinity? Current at infinity is Vs by R only. That is Vs by R. Vs by R. Okay, that is the same meaning here. Okay, that is Vs by R. Okay, no? That is energy in inductor, that is same Vs by R. Okay, now once you get about inductor, now current in resistor. Now current in resistor is same as current in inductor, same, that is Vs by R into 1 minus e power minus t by tau amperes. Then what is the voltage across resistor? Ohm's law, I into R, that is Vs into 1 minus e power minus t by tau volt. Then power is how much? Power, this is different now, Vs square by R into 1 minus e power minus t by tau whole square watts. Now energy dissipated in resistor is integral power dt, 0 to infinity. This you will get it as infinity joules. You do integration, sir. Yes, you do this 1 minus e power minus t by tau whole square, na, sir. You do that, you'll get infinity. Because upper limit is infinity, you'll get infinity. Okay, now that you remember. You'll get this as infinity. Now, efficiency of RL circuits. Here again, energy output by energy input, okay, into 100%, into 100%. But energy output is the energy stored in the inductor which can be recovered. How much it is? Half L Ia square. That is nothing but Vs by R whole square. That is half L Vs by R whole square. Here also output half L into Vs by R whole square. But losses is infinity into 100%. But something by infinity is zero, na? Efficiency of RL circuit. Let me write clearly, sir. This is RL. This is RL. Okay, na? RL circuit. Okay, so this efficiency of RL, something by infinity is 0%. 0%. Okay, that is important. Shall everyone go through this? I will explain again. This equation you have to remember. I will explain again. Okay, everybody. See, here we are talking RL circuit. State variable is inductor current. Now here, what is the meaning of energy? See, once you turn on, initially inductor will not allow sudden change. Gradually it will increase and settle to steady value. Once inductor reaches steady state, inductor acts like short circuit. But to maintain energy in inductor, current has to also maintain until infinity. Na? Unlike capacitor circuit, see in capacitor circuit, what happens? Yes, in capacitor circuit, what happened? Once capacitor is fully charged, energy can be retained in static form. But in inductor, to maintain energy up to infinity, current also has to go up to infinity. Okay, to maintain energy up to infinity, current also has to go up to infinity. If current has to go up to infinity, yes, losses also will be infinity. There is a concept here. That is why losses are infinity here. So this is the stored energy, which is output. This is output. Okay, and this is losses, and this is losses. Okay, output, and this is losses. Okay, so efficiency is 0% for RL. Okay, now There is a very, very important observation that efficiency of RL circuit is only 0%. Okay, that is very important observation, sir. Okay, that you should remember now. Now I am going with the first gate bit here. Everybody, the first gate bit. Yes. Chalo sir, listen now. This is a gate question. Find V of t for all t greater than or equal to 0. Okay, find V of t for all t greater than or equal to 0. This is 10 volt, 2 ohm, 3 ohm, 1 ohm, 2 ohm, and this is 5 amperes. 5 amperes. This is 0.1 farad. And here switch is moving from A to B at t equal to 0. Switch is moving from A to B at t equal to 0. And now I want you to determine the complete expression for voltage V. See, the switch is moving from position A to B at t equal to 0. And I want you to find the complete expression for voltage V. Yes, see now, sir, everybody listen. Here the switch is moving from position A to B. Here the switch is moving from position A to B. Okay. But the thing is, the moment the switch comes to B, source is still available. Na? Current source is still available. Previously at A position, it was interacting with DC voltage source. Suddenly when it goes to position P, it interacts with DC current source. Okay. Previously it was interacting with DC voltage source. Suddenly it go here, it will interact with DC current source. So first of all here, this is step response only. Why it is step response? Why it is step response? Yes, because after the change. Yes, because after the change it is interacting with current source. Again, what is the order? First order. Why it is first order? Only one energy storage element, capacitor. And what is the state variable? State variable is voltage only. So now we should express this. Yes, this expression V of t will be of the form. Yes, V of infinity plus V of 0 minus V of infinity e power minus t by tau. Chalo, first of all, V of 0. Now, how to get V of 0? Everybody understand how to get V of 0? V of 0, you will get, yes, V of 0, you will get, how to get V of 0? Previous steady state, na? Yes, first V of 0. V of 0, that is previous steady state. If you go to previous steady state, switch was in the left side with A, na? Yes, switch was in the left side. That means it is interacting with the voltage source. Then clearly capacitor acts as open circuit. Clearly capacitor acts as open circuit. Okay, this was interacting left side. That is 10 volts, 2 ohms, 2 ohms. Yes, it is acting like open circuit. This is V of 0. This is V of 0. Okay. Right side circuit is nowhere interacted. So V of 0 voltage division rule, it is clearly 5 volts. It is clearly 5 volts. Then V of infinity after change steady state. See, after change switch is now going to right side. Yes, it went to right side. It went to right side. Now right side again for DC steady state, you know, capacitor access open. Okay, this is 5 amperes, 1 ohm, 2 ohm, 3 ohm. Yes, 1 ohm, 2 ohm, 3 ohm. Okay, and this is V of infinity. This is V of infinity. Current cannot flow here. So this V of infinity is nothing but I into R, because this voltage itself is this voltage, na sir. That is I into R. Capacitor is open in steady state again. That is 10 volts. Chalo, V of 0 we got and V of infinity we got. But what is tau? Tau is after the change. After the change. Chalo, after the change, the capacitor will interact with the right side circuit only, na sir. But however, current source is open. So this is however 1 ohm, 2 ohm, 3 ohm. This is 0.1 farad. Okay. See, after the change, the capacitor went right side. See, after the change, the capacitor went right side. Okay, current is open. Okay, current is open. Okay, current is open, and this is how it is interacting. Okay, this is how it is interacting. Then now tau is R equivalent into C. Okay, R equivalent 5 into C. That is half second. Half second. Half second. Now, if you observe all these things, now if you observe this V of t is V of infinity, how much? 10 plus V of 0, 5 minus V of infinity e power minus t by 2, e power minus t by 2. So V of t is 10 minus 5 e power minus 2t for all t greater than or equal to 0 volts. If you plot it to understand, yes, if you plot it to understand voltage versus time, yes, at t equal to 0, it was at 5 volts. And t tends to infinity, it reaches 10 volts. Okay, t equal to 0, it was at 5 volts. T tends to infinity, it reaches 10 volts, but not suddenly, gradually with the time constant of half second. So 5 time constants, it will take 2.5 seconds to reach 10 volts. That is the meaning. See, observe these things. Okay, please observe. Again, I will tell you this expression you have to remember, sir. This expression you have to remember. First order step response in this expression. V of t, V of infinity plus V of 0. Okay. So V of 0 previous steady state, DC steady state only, V of infinity next steady state, right side circuit. Time constant after the change. After the change is the right side circuit only, na sir. Right side circuit. However, current source is open. That is the expression. Very easy bits if you know the fundamentals. Okay. They are easy bits, sir. If you know the fundamentals, they are really easy bits. Okay, na? They are really, really easy bits if you know the fundamentals. Okay. So now I am going to the next bit, everybody. This is again gate electrical, 2 marks, easy 2 marks. Find the complete expression. Find the complete expression for current I of t for all t greater than or equal to 0. He is asking like this means solution. Solution means it is transient. Okay. Ten volts, 2 ohms, 3 ohms, half Henry. Yes, find I of t for all t greater than or equal. Here switch is getting opened, please. Here switch is find. I'm writing neatly here. Yes, find I of t for all t greater than or equal to 0. Okay, find the current I of t for all t greater than or equal to 0. Find the current I of t for all t greater than or equal to 0. Okay, this is 1 Henry. I am taking this as 1 Henry only. Okay, please observe the change. I have rechanged the inductor value to 1 Henry only. Chalo, everyone try something immediately. I'm giving you 2 minutes. Okay, everybody, now listen. See here, switch is getting opened, but even then don't say this turn off process. Even though the switch is getting opened, yes, even though the switch is getting opened, but source is still available now. It is a step response concept only, please. Yes, even though the switch is getting opened, everyone should understand. Yes, even though the switch is getting opened, the source is still available. So this comes under step response only, step response only. Again, what is the order of the circuit? First order. Okay, first order. Okay, now this is the first order. Again, what is the state variable? State variable is current through inductor only. State variable is current through inductor only. State variable is current through inductor only. Okay, state variable is current through inductor. Okay, now this I of t should be of the form I of infinity plus I of 0 minus I of infinity into e power minus t by 2. So what is I of 0? I of 0 is previous steady state. Previous steady state switch was closed. Listen now carefully. When switch was closed, this resistor 3 ohms is shorted. However, for DC inductor acts like short. This is I of 0. Yes or no? This is 10 volts. This is 2 ohms and this becomes I of 0. Please understand the circuit. Switch was closed. Resistor is shorted, but inductor for DC also short now. So this I of 0 is how much? 10 by 2, 5 amperes. 5 amperes. Then I of infinity. What is I of infinity after the change? Chalo, after the change, the switch has opened. Yes, the switch has opened. The 3 ohms came again for DC inductor short. Again for DC inductor short. Okay, this is 2 ohm. Okay, this is 3 ohm. And this is I of infinity. Okay, I of infinity. Okay, again for, yes, again for DC. Yes, you know, inductor acts like short. So I of infinity is again 10 by 5, 2 amperes. 10 by 5, 2 amperes. Switch opened here means extra resistance came. Current has decreased. So this is a step decrease function. Step decrease. And now tau. Tau is after the change. See, after the change, the switch has opened. This is how the circuit will be working with inductor. However, ideal voltage source I am shorting. Okay, this is 2 ohms, this is 3 ohms, and this is 100. Because after the change, switch has opened, sir. After the change, switch has opened. Switch has opened means this 3 ohms is also there. Na? So tau is L by R, 1 by 5th of a second. So now conclusion is this I of t is, okay, I of infinity. What is I of infinity? 2. I of infinity plus I of 0, 5. I of 0 minus I of infinity e power minus t by tau. Tau is 1 by 5. So finally the answer is 2 plus 3 e power minus 5t for all t greater than or equal to 0. 2 plus 3 e power minus 5t. What does it mean? Yes, what does it mean? Let us understand the meaning here. Let us understand the meaning. Current versus time. So at t equal to 0, current was at 5 amperes. And at infinity, current reaches 2 amperes. At infinity, current reaches 2 amperes. But not suddenly, gradually with the time constant. Gradually with the time constant. Yes, this is now step decrease function. This is now step decrease function. That is the meaning here. This is step decrease function. That is what everyone should understand. This is a step decrease function. It is not step increase, this is step decrease function. Okay, it becomes 0, step decrease function. Okay, that is the meaning. Step decrease. Okay, so previously it was at 5 amperes, it decreases to 2 amperes. Okay, that is step decrease. But this is not source free concept, please. Final value is still there. This is step decrease only. Okay, na? That is the meaning, sir. Very, very interesting, but simple bit. Okay, na? Very interesting, but very, very simple bit I did. Okay. Okay, now I'm giving a fantastic gate 2 marks question. This is a gate 2 marks question, which you have to think and write. I want everyone to write this gate 2 marks question, everybody. Yes. A neon lamp. Okay, a neon lamp ionizes at 75 volts. That means it ignites. A neon lamp ionizes at 75 volts. Is connected across 1 microfarad capacitor. Okay, is connected across 1 microfarad capacitor. Now determine the value of resistance R Okay, resistance R that should be connected, that should be connected, that should be connected. Okay, that should be connected in series to this combination, to the combination already given. Okay, in series to this combination, in series to this combination. Okay, combination such that the lamp gets triggered, the lamp gets triggered. Okay, exactly after 20 seconds, 20 seconds, when an DC 100 volts supply is given to the entire circuit, given to the entire circuit. Wonderful question, sir. See, he said the neon lamp ionizes at 75 volts. Okay, the neon lamp ionizes at 75 volts. And it is connected across 1 microfarad capacitor. Determine the value of resistance R that should be connected in series to the combination. That means this R is in series to which combination? Lamp and capacitor in parallel combination. So to this lamp and capacitor, which is already parallel, to that combination, there is a resistor in series. Okay, determine the value of resistance R that should be connected in series to this combination such that the lamp gets triggered exactly after 20 seconds. The lamp gets triggered exactly after 20 seconds when a DC 100 volts is given to the entire circuit. When a DC 100 volts is given to the entire circuit. Okay, when a DC 100 volts is given to the entire circuit. So everybody try something. Write the circuit first, everybody. Write the circuit first and try, everybody. Yes, everybody listen to this problem now. See, very interesting problem. See, he said there is a neon lamp. Okay, now I'll show here. There is a neon lamp. Okay, there is a neon lamp. Okay, I will show the symbol like this. Okay, nothing wrong. Okay, neon lamp. Okay, and this ionizes when it reaches 75 volts. Okay, now it is connected across 1 microfarad capacitor. Okay, it is connected across 1 microfarad capacitor. Okay, it is connected across 1 microfarad capacitor. Determine the value of resistance R. Okay, determine the value of resistance R that should be connected in series to this combination. That is the meaning. Determine the value of resistance R that should be connected in series to this combination such that the lamp gets triggered after 20 seconds when a DC 100 volts is given to the entire circuit. Lamp gets triggered when a DC 100 volts is given to the entire circuit. So if I assume this T switch closing at T equal to 0, it should trigger after 20 seconds. Now here, until the lamp is on, it is a step response first to RC circuit now. See, until lamp is on, okay, that is our target. Then it is step response, okay, of RC circuit. Step response of RC circuit. Okay, na RC circuit. And here order is 1. Because only one energy should be. And what is the state variable? Voltage across capacitor. That voltage only will appear across lamp. Now we know this expression V of t is of the form V of infinity plus V of 0 minus V of infinity into e power minus t by tau. Now I know lamp gets triggered once voltage reaches 75 volts across it. But my expression is valid until this instant when the lamp gets triggered. But until then, if suppose this lamp is not there, final value would have been how much? Final value, that means V of infinity would have been 100 volts. But it won't reach there, I know. V of infinity would have been how much? 100 volts. Yes, if lamp is not at all there, V of infinity would be 100 volts, no doubt. But once the lamp gets triggered, it will not reach there. That I know. But yes, V of infinity without lamp is 100. But what is V of 0? No initial condition 0. V of 0, 0. Because no initial condition. Yes or no? V of 0, 0. No initial condition. Okay, na? V of 0, 0. And what is tau? Tau is RC. That is R microseconds. So this expression V of t is like V of infinity into 1 minus e power minus t by RC, R microseconds. But now he's asking us to find the R such that he's asking to find the value of R such that the lamp gets triggered after 20 seconds. So what is the triggering voltage? 75. Okay, 75. When it should reach 75? After 20 seconds. Now we can find R. Simple. So now if you observe, yes, 1 minus e power minus 20 by R micro is equal to 75 by 100. That is 3 by 4. So e power minus 20 by R micro is 1 by 4. Now, if you take logarithm, minus 20 by R micro is natural logarithm of 1 by 4. So minus 20 by R micro. Okay. Now, if you do natural logarithm of 1 by 4, everybody, yes, if you do natural logarithm of 1 by 4, it is, yes, minus 1.38, minus 1.38. Okay, now you remove minus, okay, you remove this minus and minus, okay. Then I can say this R will be 20 by 1.38 micro. Micro you take up, it becomes mega. That is 14.4 mega ohms. Okay, leave all this mathematics, but understand the concept. See, I took V of infinity as 100. I know it may not reach 100, sir. I know. Yes, I know it may not reach 100. Yes, I accept that. I know it may not reach 100. That is for true. Yes, it may not reach 100. But this expression is valid at least until the lamp gets triggered. Nah, that is my argument. I know it may not reach 100 volts. I accept. But at least this expression is valid until the lamp gets triggered. Nah, that is my strict confirmation. So at least this expression is valid until, yes, until the lamp, yes, reaches 75 volts. Okay. So V of infinity, yes, V of 0. V of 0 is not there because switch open, no voltage. Then V of infinity power minus t by 2. So triggering voltage 75, it should reach after 20 seconds. Then R is this much. Okay, R is this much. That is the meaning there. Okay. So I'm giving another interesting gate question. Everyone should do this. Very carefully listen now. Find V of t for all t greater than or equal to 0. Okay, find V of t for all t greater than or equal to 0. Okay, chalo, find V of t for all t greater than or equal to 0. Do it immediately. Everybody try it. Very important. Now everybody see, I am just asking find expression for voltage for all t greater than 0. Sir, here though is asking voltage, what is the state variable? Inductor current. So this is very important. So don't misunderstand. Though is asking voltage, first find current. Otherwise, you will not get solution. Anyone try, you will not get solution. So I will take current as state variable. So this expression for current will be, yes, I of infinity plus I of 0 minus I of infinity e power minus t by 2. So what is I of 0? What is I of 0? I of 0 is a previous DC study value. So if I take this, yes, these resistors are here, switch was open, and this inductor is shorted. Okay, this is 300 volt, 30 ohm, 30 ohm, 10 ohm, and this is I of 0. So what is I of 0? Clearly, I of 0 is 300 by 10, that is 30 amperes. 30 amperes, because parallel, now all are parallel. 300 by 30 amperes. Then, yes, then I want I of infinity. Then I want what? I of infinity. What is I of infinity? I of infinity is after closing the switch. See, after closing the switch also inductor again shorted. So this becomes something like this. Okay, after closing switch also, yes. Inductor short, and this becomes, now this time this 30 ohms won't work because inductor is shorted now. So this is 300 volt, this is 30 ohm, and this is 10 ohm, and this is I of infinity, and this is I of infinity. Okay, this is I of infinity. Okay, switch has closed, inductor short, and this is I of. So what is I of infinity? This I of infinity is directly 300 by 30 in parallel to 10. That is 40 amperes. 40 amperes. Why? Because switch closed and T tends to be inductor short. This resistor also gets short circuited. This resistor also gets short circuited. This resistor gets short circuited. Okay. Then that becomes 40 amperes. Then tau. Then tau. Tau for T greater than 0. Now, when you are finding tau, yes, when you are finding tau, yes, the effective resistance seen by the inductor. The effective resistance seen by the inductor. Yes, the effective resistance seen by the inductor. This is 30, this is 30, and this is 10. Voltage source is shorted. Now, if you observe, yes, if you observe, yes, this is one node, and this is A, this is B. So this is B, this is B, and this is B. This is A, and this is A. Now A to B 10, A to B 30, A to B 30. All are parallel. All are parallel. All are parallel. So R equivalent is clearly how much? 30 in parallel to 30 in parallel to 10. That is 6 ohms. Then tau is L by R equivalent. L is 1 by 2 by 6. It is 1 by 12th of a second. Now first state variable. Now first state variable I of t will be, yes, I of infinity. What is I of infinity? 40. I of infinity plus I of 0. What is I of 0? 30. 30 minus I of infinity into e power minus t by tau. Tau is how much? 1 by 12. So this I of t is 40 minus 10 e power minus 12t for all t greater than or equal to 0. Then what is V of t? V is L di by dt. L is how much? Half. If I differentiate this, 0 minus 10 e power minus 12t into minus 12. So this V of t is equal to, V of t is equal to 60 e power minus 12t volts for all t greater than or equal to 0. That is the answer. So don't misunderstand here. Though the question is about voltage, but current through inductor is the correct state variable. Okay. Though the question is about voltage, but the current through inductor is the correct state variable. That you have to understand. Yes, though the question is about voltage, but current through inductor is the correct state variable. That you cannot deny it. Okay, that you cannot deny it. Okay, that you please understand. Okay, that you cannot deny it. Okay, that is very, very interesting. That you have to understand. Okay. Now I am going further. Okay. Now once we got this, yes, everybody. Once we got this, I am going further now. So now this is another question. Find maximum value of, find maximum value of V, find maximum value of V. This is 10 million. This is 6 milli. Okay, let me tell, because all combinations I'm thinking, sir, some random values. Chalo, now, sir, everybody should do. Yes. Find the maximum value of voltage V. Find the maximum value of voltage. Okay, everybody. See now, I am asking what is the maximum value of V. See, actually, V is the mutual voltage induced in coil 2 because of current in coil 1. Na? Yes, V is the mutual voltage induced in coil 2 because of current in coil 1. So, first I will find this current I. Okay, I. Now, because this is step response first order RL circuit, this I of t will be of the form I of infinity plus I of 0, okay, minus I of infinity e power minus t by tau. So, in that regard, if I go, now clearly here I of 0 is how much? I of 0, 0. I of 0 is 0. Yes or no? But what is in I of infinity? In DC steady state inductor short, I of infinity is 20 by 4, which is 5 amperes. This is also 20 by 4, which is 5 amperes. And what about tau? Tau is L by R. Tau is L, 8 milli by R. That is 2 milliseconds. 2 milliseconds. Okay. So first, if I take this expression for current, yes, this current I of t will be, yes, that is nothing but, yes, 5 into 1 minus e power minus t by tau. Okay. And this is 2 milli, that is minus 500 t. Okay, because t by tau. T by tau. Tau is how much? 2 into 10 to the power of minus 3. That is 1000 by 2 minus 500 t. Okay, na? Yes, we got I. Then what is this V of t? Mutual voltage, na? V of t, mutual voltage, but polarity. If current enters, see here, if current enters the dotted terminal of first coil, if current enters the dotted terminal of first coil, then the polarity of the mutual voltage is positive at the dotted terminal of second coil. If current enters the dotted terminal of first coil, this current, then the polarity of the mutual voltage is positive at the dotted. So reference polarity is positive. Plus mutual voltage is how much? 6 milli into d by dt of this I of t. Yes. Now if you expand this, this V of t is equal to 6 milli into differentiation of this current, sir. That is first 5 is there. 5 is there into 0 minus. Okay, 0 minus. Yes, if you differentiate this, e power minus 500 t, e power minus 500 t into minus 500. So V of t will be, okay, this is 6 5s are 30. Okay. And this is again minus 500. Don't forget this. Okay, this is again minus 500. Okay, so this is already 6 5 is 30 into milli is there, don't forget, into 500 into e power minus 500 t, minus minus plus na. So milli and this 500 if you remove, chalo, milli and this 500 if you 530 remove, that becomes 15 3 by the 15 e power minus 500 t. So now what is Vmax? Vmax is at a t equal to 0. Vmax is at t equal to 0. That is equal to 15 volts is the answer. Wonderful question. Check it out. This is magnetic circuit with transient, sir. Check it out, the meaning. Magnetic circuit with transient. Okay, this is magnetic circuit with the transient. Magnetic circuit with the transient. Okay, so this is step response first order RL in the left side. Secondary is open now, sir. There is no mutual voltage now, but mutual voltage will be induced in the secondary because of the primary current, but there is no mutual voltage in the primary because of secondary current, because secondary is open circuited. So if current enters the dotted terminal of first coil, then the polarity of the mutual voltage is positive at the dotted of second coil, and that is how we got the answer. Okay. Yes. Now I'm going to another interesting gate question. Find I of t for all t greater than or equal to 0. This is 100 U of t volt. This is 10 ohms, 20 ohms. This is current I. This is 20 I, and this is 100. So I want this current I. Okay, then let me take this as Ix. This is 20 Ix. Okay, chalo. So find the complete expression for this current in the inductor only, sir. I am asking. Yes, current in the inductor. Okay. Determine current I. Now, sir, this is now see this. What is the meaning of this 100 volts? This 100 U of t means this is step voltage. 100 U of t is different now, not like the previous problem with 20 U of minus t was source free, but this is 100 U of t means 100 volts is suddenly given at t equal to 0. 100 volts is suddenly given at t equal to 0. Okay, I'm giving 100 volts suddenly at t equal to 0. Okay, that is the meaning. This is 100 volts. Okay, yes, that is the meaning. You are giving suddenly 100 volts at t equal to 0. Yes, you are giving suddenly 100 volts at t equal to 0. See here, sir, everyone. Good, sir. Some students are trying. I'm very, very happy for them. I'm really happy that some students are really trying their hard. Now here, if you observe, this is step response, sir. This is no doubt step response, turn on process, because 100 U of t means 100 U of t means here 100 volts is given. 100 volts is given. So this is no doubt step response first order RL circuit. Again, this expression for current. Yes, this expression for current will be of the form. Yes, I of t is I of infinity plus I of 0 minus I of infinity into e power minus t by tau into e power minus t by tau. So now first I of 0. If I first go to I of 0, yes, if I go to first I of 0, that means DC steady state. It is not there now, no source. It is 0. Because why? Because there is no source now. There is no source. I of 0 is 0. Because when no 100 volts was given, before that nothing was there. Dependent source, however, cannot work. So now I of infinity. Now if I go to I of infinity, this is DC steady state. Now 100 volts DC is given. Yes, 100 volts DC is given. Inductor short. Yes, this is what happens in steady state finally. Initially I of 0, 0. This is I of infinity. Now this is clearly 100 volts DC, 10 ohms, 20 ohms, plus and minus 20 ix, and this is ix. This is ix. Now I want what? Yes, I want this I of infinity. I want this I of infinity. Now this is 100 by 10. This is 10 amperes. Ix is 10. So this becomes how much? 200 volts. 200 volts by 20. This is another 10 amperes. Now if you apply KCL, that is 10 plus 10 is 20, which is our I of infinity. See what, sir, what I did. So I of infinity means DC steady state, na sir. DC steady state, inductor acts like short. When 100 volts is given suddenly, I of 0, 0, no voltage was given. I of infinity is 100 volts is given as steady. So when DC steady, this inductor short. Now see, the only resistance seen by this 100 volts is 10, because this is shorted, na. So 100 by 10, 10 amperes. If Ix is 10, this becomes 20 Ix, 200 volts. Now the only resistance seen by this dependent source is externally 20. So 200 by 20, that is another 10. So KCL, 10 plus 10 is total 20. So I of infinity is 20. Okay, I of infinity is 20. Now tau, sir. Now tau for t greater than 0. Now there is a challenge. Yes, tau for t greater than 0, that is a challenge. Okay, tau for t greater than 0. Now if you observe that, now I want the R equivalent seen by the inductor after the change. I want to see the R equivalent seen by the inductor after the change. Yes, I want the R equivalent seen by the inductor after the change. So this is clearly 100 volts given, 10 ohms, 20 ohms. This is Ix. This is plus and minus 20 Ix. Okay, I want the R equivalent seen by the inductor. R equivalent seen by the inductor. Okay, I want the R equivalent seen by the inductor. Okay. Now here clearly, yes. Now this is Thevenin's category 2. Yes, Thevenin's category 2. Because independent dependent source are there, we will go with procedure. This is Thevenin's category 2. So R equivalent will be VOC by ISC. I will go with procedure, sir. Okay, VOC by ISC. Step 1, VOC. Now if I go with VOC, same problem. See here I am taking again. This is now 100 volt, 10 ohm, 20 ohm, Ix, plus and minus 20 Ix. Now first VOC. This is VOC. Okay, now if you observe VOC, first I will write a big mesh equation. Chalo, first I will write a big mesh equation. Then I will write a KVL. First, if I write the mesh equation, minus 100 plus 30 Ix. Because 20 plus 10 series now, because open, 30 Ix plus 20 Ix is 0. From that, Ix is 2 amperes. Now, if I write another KVL, minus 100 plus 10 Ix plus VOC is 0. From that, VOC equal to 100 minus 10 Ix. Now, if you solve 1 and 2, so now if you solve 1 and 2, VOC is 100 minus 10 into 2, 100 minus 20, VOC is 80 volts. VOC is 80 volts. Okay, now step 2, ISC. Step 2, ISC. But sir, but here in this problem, ISC means this circuit only will come now, sir. See, actually we should short this. ISC will be this circuit only now. In this case, ISC is I infinity. Okay, ISC is I of infinity only. That is 20 amperes. 20 amperes. ISC is I of infinity is 20 amperes. Then what is R equivalent? R equivalent is VOC by ISC. Okay, VOC is 80. ISC is 20. So that is 4 ohms. Then finally tau. Tau is L by R equivalent. Okay, L by R equivalent. L how much I took? 1. R equivalent is 4. So now finally I of t is I of infinity. Okay, plus I of 0, 0 minus I of infinity e power minus t by tau. Okay. So finally this I of t is 20 into 1 minus e power minus 4t for all t greater than or equal to 0. Okay, this is for all t greater than or equal to 0. Okay, now yes, we'll take a 10 minutes break, everybody. Chalo, take a 10 minutes break. We'll start category 3 now. Very, very important it is. Okay, we'll take a 10 minutes break and then we'll have a category. Yes, 10 minutes break, everybody. Okay, I will make it 15 minutes. Okay, to 12:10, 12:10 you come. 15 minutes break, everybody. Yes, everyone. So we completed all the models in category 2 also. Okay, what is category 2? Yes, category 2 was step response of first order circuit. What is category 2? Step response of first order circuit. Okay, na? Okay. Now let us go to category 3. Now listen, sir. This is going to be now lot of mathematics is coming. Category 3. This is source free. I want everyone to listen. Source free second order circuits. Okay. That too first let us learn standard. That is in that A, series RLC. Series RLC. Now this is also turn off process. Source free na turn off process. Series RLC. Okay. RLC. Now here, how can this circuit work even without source? Yes, this circuit can work even without source, provided there is some initial energy either in inductor or in capacitor or in both. Okay. This circuit can work again even without source. Yes, this circuit can work even without source, provided there is some internal stored energy either in inductor or capacitor or both. Okay. Either in inductor or capacitor or both. Okay, na? That is the meaning. Yes, either in inductor or capacitor or both. Okay, depends. If only inductor energy, that also will drive. If only capacitor energy, that also will drive. Both also can be there. Again, there are two possible state variables. What are the two possible state variables? One is inductor current and one is capacitor voltage. Again, you can take anything. Because it is series, I prefer taking current, sir. Current through inductor. So here I say the preferable state variable is current through inductor. Because once you get the state variable current, then finding voltages are easy. Okay, na, from Ohm's law. Now, because it is inductor current as state variable, so I will write a KVL. If I write a KVL, IR plus LdI by dt plus 1 by C integral I dt equal to 0. If you differentiate again, LD square I by dt square plus R di by dt plus I by C equal to 0. So this is a second order differential equation gone in the system. Now, the moment you come to second order, I'll better use Laplace for mathematical simplicity. I will use Laplace. Okay, use Laplace transforms. Okay, use Laplace transform. Then I will do this L s square I of s. Okay, plus R s I of s plus I of s by C equal to 0. Okay, na? L s square I of s, R s I of s plus I of s by C equal to 0. Now, if you take I of s common, s square plus R by Ls plus 1 by Lc equal to 0. Okay, s square plus R by Ls plus 1 by Lc equal to 0. Since I of s cannot be 0, so this has to be 0. S square plus R by Ls plus 1 by Lc has to be 0. This is the characteristic equation governing the second order series RLC circuit. Now here, the two roots of this characteristic equation will determine the nature of response, where S1, S2 are minus B plus and minus root of B square minus 4AC by 2A. All this, if you do, you will get something like this. Okay. Now let alpha is R by 2L. Okay. So this alpha is R by 2L. This is called damping factor or damping coefficient. Damping coefficient, not damping ratio, please. And omega naught is, however, 1 by root LC. We already know the answer. Omega naught is natural frequency, which is resonance frequency. This is called undamped natural frequency. Okay. So now I will write the roots as, roots I will write like, okay, S1, S2 is equal to minus alpha plus and minus root of alpha square minus omega naught square. Go through this, everyone. Go through this. Once you just 3, all mathematics, sir. All mathematics is telling the story here. Okay, so this is second order differential equation. So I used Laplace immediately, characteristic equation, roots. But this R by 12, I will call it as damping factor or damping coefficient. See, damping ratio zeta is different. That is in controls R style. And omega naught is undamped natural frequency. So roots I wrote. Now here, based on the values of RLC, we have 3 types of responses. So case 1, if alpha greater than omega naught, okay, that is called overdamped response. That is R by 2L is greater than 1 by root LC. That is a condition. Okay. Now here the two roots are negative, real, and unequal. Okay, the two roots are negative, real, unequal. Okay, the two roots are negative, real, and equal. Then this response for current I of t will be of the form A1 e power S1t plus A2 e power S2t for all t greater than or equal to 0. This link comes from where? This links come from differential equation. So differential equation in mathematics is telling this. Here, only thing I want to write is here A1 and A2 are constants. Yes, are constants that can be determined from initial conditions. Okay, A1, A2 are constants that can be determined from initial conditions. Okay, A1, A2 are constants that can be determined from initial conditions. Case 2, if alpha equal to omega naught. This is called critically damped, where R by 2L equal to 1 by root LC. R by 2L equal to 1 by root LC. Okay, then the two roots are negative, real, and equal. The two roots are negative, real, equal. Then this current I of t equal to e power minus alpha t A1 plus A2t. This is for all t greater than or equal to 0. Okay, this is for all t greater than or equal to 0. This expression will come. Okay, then case 3, that if alpha is less than omega naught, this is called underdamped, where R by 2L is less than 1 by root LC. Okay, R by 2L is less than 1 by root LC. Okay, then the roots are, okay, complex conjugate with negative real part, okay, negative real part. Then the response for current I of t is like e power minus alpha t A1 cos omega dt plus A2 sin omega dt. However, we know A1, A2 are arbitrary constants. but this alpha is called damping factor. This omega d is something interesting. Here extra thing is, here omega d is root of omega naught square minus alpha square. Here omega d is root of omega naught square minus alpha square, which is called damped. It's called damped, okay, or forced or ringing frequency. Ringing frequency. Okay. Here omega d is called root of omega naught square minus alpha square, damped, forced or ringing frequency. Now if I plot this, okay, approximate plots, how they look. Now we are observing current versus time. Okay, state variable current na current versus time. But where this current will start, that depends upon initial condition. Okay, current where it is starting, that depends upon initial condition. That depends upon the problem. But current response is going in three ways. One is overdamped, sluggish, slow and sluggish. Okay, slow. Yeah, sluggish means slow. Very, very boring type of response. It will take a lot of time to set. That is overdamped. Next is critically damped, quick, but without any oscillations. Quick, but without any oscillation. This is critically damped. Then the last one is under much faster, but with lot of internal oscillations. Okay, this is much faster, but with lot of internal oscillations. These internal oscillations are called as damped frequency. Okay, so this is overdamped, this is critically damped, and this is underdamped. Okay, that means in this source-free second order, the response for current can be of three types based on the values of RLC. Okay, now, so what is the meaning? See, in first order circuits, only one type of response came, sir. Exponential decay, that's it. But in source-free second order, based on the values of RLC, three types of responses came. Either overdamped, which is this outermost yellow line. Okay, then it can be either critically damped, quick but without oscillations, or finally underdamped, lot of internal oscillations. Okay, that is how the response can go in three possible phases. That is the meaning. Now let us also give the mathematics for parallel RLC. Very, very important, sir. Parallel RLC network. Okay, now if I go to parallel RLC, yes, R L C, yes, parallel RLC. Yes, everybody watch RLC. First of all, here also the circuit can respond even without source, provided either inductor as initial condition or capacitor as initial condition. Okay, circuit can respond even without source, provided either inductor as initial condition or capacitor as initial condition, or both. Okay, again, there are two possible state variables. One is inductor current and capacitor voltage. But here I prefer to take voltage across capacitor state variable, because voltage is constant in a parallel circuit. Voltage is same in parallel elements. Then I can find current separately. So here my preferable state variable is voltage across capacitor. Then I will write nodal equation, KCL nodal equation. Okay, if I write the nodal equation, this is V by R plus 1 by L integral V dt plus C dV by dt equal to 0. Now if I differentiate again, C d square V by dt square plus 1 by R into dV by dt plus V by L equal to 0. So this is a second order differential equation gone in the system. Okay, second order differential equation gone in the system. Okay, now this is a second order differential equation. Now if I use Laplace transform, use Laplace transform. Yes, if you use Laplace transform, C s square V of s plus s by R into V of s plus V of s by L equal to 0. So if I take V of s common, s square, okay, plus 1 by RCS, okay, or s by RC plus 1 by LC equal to 0. But since V of s cannot be 0, this has to be 0. S square plus s by RC plus 1 by LC has to be 0. Has to be 0. Okay, this is called the characteristic equation gone in the system. This is called the characteristic equation gone in the system. Okay, what this is called? This is called the characteristic equation gone in the system. Okay, so here again the two roots. Here again the two roots. The two roots S1, S2 are minus B plus n minus root of b square minus 4ac by 2a. You do that, you will get this. So here again, yes, here again, let alpha is 1 by 2 RC. This is called as damping factor or damping coefficient. Damping factor or coefficient. Okay, damping factor or coefficient. And omega naught is 1 by root LC. Undamped natural frequency. Now the roots I can write it as S1, S2 is equal to minus alpha plus and minus root of, okay, minus alpha plus and minus root of, okay, plus and minus root of alpha square minus omega naught square. Okay, that is the meaning. Where alpha is 1 by 2 RC, omega naught is 1 by root LC. Okay, na? That is the meaning. That is the meaning here. Okay, that is the real meaning here. Okay, now here also based on the value of RLC, we have three types of response. So case one, here also if alpha greater than omega naught, this is called what? Overdamped response. Overdamped response. In overdamped response here 1 by 2 RC should be greater than 1 by root LC. That is the meaning. Then the two roots are, okay, negative, real and unequal. Negative, real and unequal. Okay, the two roots are negative, real and unequal. Okay, then this expression for voltage V of t is like, yes, A1 e power S1t plus A2 e power S2t for all t greater than or equal to 0. Okay, here again A1, A2 are the constants that we can determine. Yes, A1, A2 are constants that we can determine by initial conditions. Case 2, if alpha equal to omega naught, this is called critically damped. Critically damped. Critically damped means 1 by 2 RC is equal to 1 by root LC. The two roots are negative, real and equal. Negative, real and equal. Then this V of t is e power minus alpha t A1 plus A2t for all t greater than or equal to 0. Okay, for all t greater than or equal to 0. E power minus alpha t A1 plus A2t for all t greater than or equal to 0. Okay, now then case 3. Case 3, if alpha less than omega naught, this is called underdamped. 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 Okay, that is 1 by 2 RC is less than 1 by root LC. Okay, then the two roots are complex conjugate with the negative real part. Then this, yes, then this V of t is e power minus alpha t A1 cos omega dt plus A2 sin omega dt for all t greater than or equal to 0. But here again, you remember this omega d is called what? Damped frequency. This omega d is root of, okay, omega naught square minus alpha square, which is called damped or forced or ringing frequency. All the terms are ringing frequency. Now, if I approximately plot it, voltage versus time, if I approximately plot it, yes, voltage versus time, yes, voltage versus time. Where it is starting, it depends upon the initial condition. It depends upon initial condition. But it will go in three possible ways. Overdamped is sluggish, slow. Critical damp is faster, yes, slightly faster, but without any oscillations. then under damped much faster, but with lot of internal oscillations. Okay, lot of internal oscillations. Okay, this is for over damped, this is for critically damped, this is for under damped. Okay, if alpha less than omega naught, it is underdamped. That is 1 by 2 RC is less than 1 by root LC. The roots are complex conjugate with negative real part. Okay, so one thing we concluded that in series RLC, now comparison, sir. See here, in series RLC, I took current as state variable, inductor current, and for that current, there are 3 types of responses based on the values of RLC that you remember. Okay, overdamped, critically damped, underdamped. And in parallel RLC, yes, I took voltage as state variable. And again, based on the values of RLC, 3 types of responses for voltage here. There is a big difference. Okay. Now to understand this mathematics, yes, everybody to understand this mathematics. Now look at this first simple observable IES object. This is an IES object we are writing. Okay. The response, please observe, sir. This is only mathematical bits, formula bits. We will understand a lot of things, sir. The response for current I of t for all t greater than or equal to t is dash. Okay. So the response for current I of t for all t greater than or equal to 0 is dash. See, asked like this. Okay, this is some 20 volts, 2 ohms, 1 Henry, half farad. And this is the current I'm asking. Okay, the response for current I of t for all t greater than 0. Options are overdamped, B, critically damped, C, underdamped, D, sinusoidal. Shall everybody write some answer? Very interesting. Write some answer, everybody. See, the switch is moving. Clearly here, the switch is moving from position A to B. That is the meaning, sir. I will write neatly again. The meaning here is the switch is moving from position A to B. The switch is moving from position A to B at t equal to 0. A to B. Okay, the switch is moving from position A to B. Okay, the switch is moving from position A to B. Chalo. The response for current I of t is dash. Over damped, critically damped, under damped, sinusoidal. See, such bits are important, sir. Yes, everybody now see, listen. See, when the switch is coming from A to B, that means switch position will come here. Yes or no? That means previously it was there. Now it will come here. Now once it comes here, it will become source free. Now it isolates from the source and becomes a series RLC, source free series RLC. Yes, once for t greater than 0. So if you observe here, for t greater than 0, switch comes at position B, then it becomes source free series RLC. Yes, series RLC. That is the meaning. Why? See, once switch was at A, it was already in the previous steady state, that is DC steady state. Once the switch comes to B, source is isolated, source is removed. So it becomes a source-free series RLC. Now in source-free series RLC, the state variable inductor current has 3 types of responses based on the values of RLC. So first, let us calculate alpha. Alpha is R by 2L. Now, if you observe R by 12, R is 2. Okay, R by 12, if you observe, yes, R is 2, L is 1. So this is 1. Omega naught is 1 by root LC. Omega naught is 1 by root LC. 1 by root L is 1, C is 1 by 2. That is root 2. So clearly alpha is less than omega naught. Alpha less than omega naught means it is underdamped. Yes, sir, underdamped. Everyone should understand this is what? Underdamped. So I will take the answer underdamped. Okay, the current will oscillate, sinusoidally oscillate with, or I can say exponentially decaying oscillations. Okay, what is the meaning of underdamped? You see, no, underdamped meaning is, yes, underdamped meaning is it will oscillate sinusoidally and decay. Okay, decayed oscillations, I will say. Decayed oscillations. That is how the current will go in this circuit, decayed oscillations. Okay, now then everybody, I'm giving another IES objective. Okay, the response for V of t greater than or equal to 0, t greater than or equal to 0 is like dash. Okay, observe this question also very carefully. This is 2u of minus t amperes, half ohm, 1 Henry, 1 farad. Okay, 2u of minus t amperes, half ohm, 1 Henry, 1 farad. Okay, half ohm, 1 Henry, 1 farad. And these are the options he gave. Voltage versus time. Option A, option B, option C, option D. This is like this. This is like this. Okay, chalo, take the correct answer. The response for voltage V of t is like dash. The response for voltage V of t is like dash. The response for voltage V of t is like dash. Yes, I'm getting interesting answer now. See, sir. See, what is the meaning of 2u of minus t? 2u of minus t means this volt current source is becoming 0. Current source becoming 0 is replaced by short open circuit now. Please understand. I'm repeating. See, 2u of minus t means current source is becoming 0 at t equal to 0. Current source 0 means open circuit. Voltage source 0 means short circuit. So here for t greater than 0, yes, it becomes a source free. For t greater than 0, this becomes what? Source free parallel RLC. Parallel RLC, standard circuit. Formulas are there. Yes or no? Source free parallel RLC. Yes or no, sir? Please observe, sir. Because the moment current becomes 0, open. The moment current becomes 0, open. If voltage source becomes 0, short. But if current source becomes 0, open it. So for t greater than 0, current source 0. So I can replace it with the open circuit. So it becomes source free second order parallel RLC. Now here the nature of response for voltage can be in 3 ways based on the values of RLC. alpha. Alpha is 1 by 2 RC. That is 1 by 2 into R into C. That is 1. Omega naught is 1 by root LC. That is 1 by root. L is 1. C is also 1. That is 1. So clearly here, alpha equal to omega naught. Alpha equal to omega naught. This is critically damped. Chalo sir, now see critically damped. First of all, oscillations won't come in critically damped. This is undamped sinusoid. This is not answer, and underdamped also oscillation. But out of these two, which to select? In critically damped, settling time is smaller. Listen now, sir. See, in critically damped, settling time is smaller than overdamped. In critically damped, settling time is smaller than overdamped. So option is D. Why option is D? Here less settling time. Here less settling time. That is very interesting, na sir. Less settling time. Settling time. Okay. Overdamped is more sluggish, but critically damped has less settling time. So option is D. Option is D. Very interesting. Okay. Now I am asking interesting question given in IES. Okay. What is the time constant? What is the time constant of the circuit below? This is very interesting question. Circuit below. What is the time constant of circuit below? Okay. Your switch is getting opened. 30 volts, 2 ohm, 3 ohm, 1 ohm. Okay, this is 1 by 4 farad and 1 Henry. So what is the time constant circuit? Please observe I'm giving the solution now. Just observe, I'm giving the solution now. Yes, what is the time constant of the circuit shown below? Okay, what is the time constant of the circuit shown below? Everybody please understand what is the time constant of the circuit shown below. Okay, now see, to understand this, let us go to some fundamentals. Listen now carefully, sir. See, second order, actually, let us see this. First of all, in the given circuit, here switch is getting opened or closed. Yes, switch is getting opened. Here switch gets opened. Yes or no, sir? Everybody? Yes, here. Yes, here switch gets opened. Switch gets opened. Yes, when switch gets opened, then it becomes a source free. Yes, source free second order series RLC circuit. Series RLC circuit. Okay, it becomes a source free second order series RLC because the moment switch is opened, please observe. See, I remove all this. Switch is open. That 1 ohm is also waste na. That 1 ohm is also waste. Now it becomes a series RLC na. Yes, it becomes a source free second order series RLC. Yes or no? It becomes a source free second order series RLC. Yes or no? So now in source free second order, there is an approximate time constant. We have approximate time constant. Approximate tau value. Let us see how. Now for that, if you see here, everybody, if you see in the case of critically damped and underdamped, in the case of critically damped and underdamped, because the response is like e power minus t by tau into function. Here tau is approximately 1 by alpha. But already what is alpha? Yes, we know alpha is how much here? R by 2L. So this approximately becomes 2L by R seconds. 2L by R seconds. So in a series RLC source free, this is, and even in the case of underdamped, this I can write tau is e power minus t by tau. Tau is approximately 1 by alpha. That is 2L by R seconds. Remember, sir. But what about overdamped? Now in overdamped, we know the roots are negative, real, and equal. Suppose imagine the roots are like this. Suppose imagine roots are one is -1, one is -4. Okay, one is -1, -4. If it is -1, -4, yes, if it is -1, -4, this becomes how much? -1 and -4. So e power -4 is negligible. E power -4 is negligible to e power -1, na, sir? Yes, e power -1, -4 value is negligible when compared to e power -1. So that means this is negligible. This only will dominate. So dominant pole, this is called dominant pole. The dominant pole will decide. So here the approximate time constant is minus of 1 by dominant pole. This concept will come in control system also, sir. See, in overdamped, already controls is happening now, sir. There you can link this. In overdamped, the roots are negative, real, and equal. Suppose let us say the roots are -1, -4, because negative, real, and equal. Na, out of this, which is called dominant pole, which is nearer to the imaginary axis. The dominant pole is nearer to the imaginary axis, which is -1. If you substitute, this becomes e power minus t, e power -4t. But e power -4t is negligible when compared to e power -t. Na? So this is negligible. So time constant is given by minus of 1 by dominant pole. Okay, remember this. Similarly, in parallel also, everybody see in parallel also. Now for critically damped and underdamped, critically damped and underdamped, is the approximate time constant is, because it is of the form e power minus t by tau 1 by alpha. But in RLC, see parallel, RLC parallel, what is alpha? 1 by 2 RC. So this becomes approximately 2 RC seconds, 2 RC seconds. Here also, tau is approximately 1 by alpha, which is approximately 2 RC seconds, 2 RC seconds. But however, in the case of overdamped, the approximate time constant is minus of 1 by dominant pole, dominant pole. Okay, so remember, sir, this yellow formulas just now I gave. Now listen to this. So here, first of all, this becomes a source-free second order circuit, series RLC, and we have approximate time constant. So for that, let us observe the nature of the network. So first of all, here, what is alpha? Here alpha is R by 2L. Series RLC, na? Yes, R by R is what? 2 plus 3. R is how much? 2 plus 3, total 5 by 2 into L. But what is L? L is 1. L is 1. So this is 2.5. Omega naught is what? 1 by root LC. 1 by root LC. L is 1, C is 1 by 4. L is 1, C is 1 by 4. That is nothing but 2. So clearly alpha greater than omega naught. Alpha greater than omega naught. So this is really what? Overdamped response. Overdamped response. Okay, overdamped response. Now for overdamped response, we already learned just now. See, for overdamped response, minus of 1 by dominant pole, minus of 1 by dominant pole. Okay, so first of all, roots we will find. Roots S1 is to R. Okay, minus alpha plus and minus root of alpha square minus omega naught square. So that is minus alpha 2.5 plus and minus root of 2.5 square minus 2 square. So this become minus 4 comma minus 1. So which is called dominant pole? This is called dominant pole, dominant pole. Now the time constant is approximately minus of 1 by dominant pole. That is minus of 1 by minus 1. So time constant is 1 second. See that interesting question in IES. See, today morning we were studying double inductor problem. Now in double inductor problem, there lumping is not possible. There is no single time constant. But here for series RLC standard circuit and for parallel RLC standard circuit, mathematically approximate time constant exists. And that is how we are finding mathematically. And here in this case, the answers are this. Okay, answers are this. Okay, na? Yes. So please observe. Now, yes, before I close, I'm just giving the formulas for category. See, category 3 is not over, sir. Category 3 solution we will start tomorrow, but I will just give the formulas 2 minutes for category 4 also. Just listen now carefully. See, category 4 formulas are important. That will save time tomorrow, sir. This is step response of second order circuits. Second order circuit. Quick, sir. In 2 minutes, I will complete. So now here, this is turning on process. Okay, this is turning on process, but it is second order. R, L, and C. Okay, this is step response of second order circuit. Okay, this is step response of second order circuit. This is, okay, first DC transients only we are studying. AC transient I will teach you at last. So you are turning on at T equal to 0, R, L, C. Now here, this is turning on process. That is why we call this as step response. Okay, and again, there are 2 possible state variables. One is inductor current, capacitor voltage. But here I will take the dominant state variable is voltage across capacitor only. The dominant state variable is voltage across capacitor only. Why? Because in steady state current becomes 0, na, sir. In steady state current becomes 0, then I cannot show steady state value, na. See, in this series RLC circuit for DC excitation, Yes, in this series RLC circuit for DC excitation, in steady state capacitor acts as open. When capacitor acts as open, current becomes zero. So if I take current as state variable, I cannot show current in final value. So the dominant state variable is voltage across capacitor only. Then I can say this total response is forced response steady state plus natural response transient state. Okay. First, let us write. First, V steady state is at t tends to infinity. T tends to infinity. Now, if I go to t tends to infinity, switch has closed. Okay, inductor short, capacitor open. Inductor short, capacitor open. Okay, this is Vs and this is R and this is V of infinity. V of infinity. Okay, V of infinity. So this becomes how much? Vs only. This becomes how much? Vs only. Okay, but V transient of t. V transient of t depends upon RLC. RLC. Where again alpha is R by 2L, which is called damping factor, and omega naught is 1 by root LC. Okay, undamped natural frequency. Undamped natural frequency. Okay, na? So now, if you observe both, if you add both, na sir. So if you add both, everybody, if you add both, then I will write total response is just formula, sir. Total response is, okay, total response is this V of t can be in three ways. Okay, one is V steady state. V steady state, how much we got? Vs only now in this case. So V steady state plus V transit. One is A1 e power S1t plus A2 e power S2t. This is for what case? Alpha greater than omega naught. Alpha greater than omega naught, which is called overdamped case. Overdamped case. Or other response is Vs plus e power minus alpha t A1 plus A2t for alpha equal to omega naught. This is for critically damped case. Critically damped case. Okay, or this Vs plus e power minus alpha t A1 cos omega dt plus A2 sin omega dt. For alpha less than omega naught, for alpha less than omega naught, this is for underdamped case. Underdamped case. Okay. Now, if I just show the nature of the graph, yes, if I just show the nature of the graph approximately, where it starts this voltage, because why I took voltage only? Because voltage across capacitor exists in steady state. If I take inductor final value becomes zero, then again it looks like a source free. Mathematically it looks confusing. So I took capacitor voltage as state variable because final value exists. That is why it's called dominant state variable. Okay, so now it starts from somewhere initial condition, but it reaches to final value Vs, that is steady state na Vs. But in what possible? Three ways. One is overdamped, sluggish. One is critically damped, quick and fast. One is underdamped, much faster, but with lot of internal oscillations. Okay. So this is for overdamped case. This is for critically damped case. And this is for underdamped case. Okay. So please just mathematics we will learn. This is what a step response of second order in that A. Okay. This is A. This circuit is A. That is for series RLC. This circuit is A. That is series RLC. For series RLC circuit, I give series RLC circuit. Okay, now I'm concluding B. Okay, parallel RLC circuit. Last topic for today, parallel RLC circuit. Okay, if I go with parallel RLC, this time, yes, I am showing the same concept, but for a change, I am showing such things like here, I will give current source as input. Otherwise, unnecessary confusions will come. And I am showing switch open dual concept. Okay, switch open at t equal to 0 will allow the current to flow. Current to flow. RLC. Now here again, there are two possible state variables, but you tell me, sir, which state variable can exist as t tends to infinity? Everybody tell me which state variable can exist as t tends to infinity? Which? No, we'll complete, sir. No, we'll complete. Don't worry. Which state variable will exist as t tends to infinity? Which state variable can exist as t tends to infinity? See, in DC steady state, inductor short, capacitor open. Inductor short, capacitor open. If inductor short, capacitor open, voltage across short circuit cannot exist. So only inductor current can exist. So the dominant state variable is inductor current only, because capacitor voltage finally becomes zero as inductor is shorted. That is why if I take capacitor voltage, nothing wrong, but you cannot express steady state. Now again, we know This total response is forced response, which leads to steady state, plus natural response, which leads to transient state. Now, first let us write, yes, first let us write I steady state at t tends to infinity. Now, if I go to t tends to infinity, switch has opened, current source came, and for DC current source, inductor acts like short circuit, capacitor acts like open circuit. Capacitor acts like open circuit. This is R. So, this is I of infinity. So what is this I of infinity? Resistor is shorted, now full current will go. That is IS only. I of infinity become IS only. But I transient of T. But I transient of T again depends upon RLC. Depends upon RLC values, where alpha here is 1/2 RC. Yes, here alpha is 1/2 RC because parallel na, and omega naught is 1/root LC, which we studied in category 3 only. We are attaching that. So steady state plus transient become total response. Okay, so this response, so finally the total response is okay, I of T is I steady state. I steady state is IS plus A1 e power S1T, A2 e power S2T. Okay, this is for alpha greater than omega naught, which is called what, sir? Overdamped case. Which is overdamped case. Or another possible response is, yes, another possible response is IS plus e power minus alpha T. Okay, A1 plus A2T. This for alpha equal to omega naught. Alpha equal to omega naught, which is called critically damped case. Critically damped case. Critically damped case. Or this IS plus e power minus alpha T. A1 cos omega dt plus A2 sin omega dt for alpha less than omega naught. Okay, this is called underdamped case. Underdamped case. Underdamped case. So if you just plot approximate graph, it looks like this, but this time current is the state variable here. Okay, where it starts from initial conditions. Where it reaches a steady value IS, but in three possible ways: either overdamped, critically damped, or even underdamped with lot of oscillations. So this is overdamped case, this is critically damped case, this is underdamped case. Okay, chalo, we'll close everything here, sir. We'll close everything here. Okay, okay, sir. Lead and come. See, tomorrow you'll enjoy the class when you read all these things and come. Okay, this category 3, category 4, only formulas I gave, don't worry. See, this category 3, category 4, what I gave in the last 1 hour is a lot of mathematics. So at least learn that formulas and come. See all this differential equation using Laplace, roots, based on the roots, 3 types of response. Okay, then parallel RLC, source free, first voltage I took as state variable, then again 3 types of response. But in I took some sample problems, how such bits come, how such mathematical bits can come, and concept of time constant also. Then for step response, here in series RLC, voltage is state variable because final value exists for voltage only, current becomes 0. And again, voltage can be in 3 types, I plotted approximately. And for parallel RLC, state variable is current because current only can exist as infinity because voltage across capacitor becomes 0 as inductor is shorted. So better take current as dominant state variable. Again, 3 types of response based on the values of RLC. Okay, based on the values of RLC, and I plotted it. Okay, na? Chalo, tomorrow again 7 o'clock, but doubts. Usha, what is your doubt? Usha, what is your doubt? Okay. Bimal is fine.
That question in the energy storing, you are calculated direct by taking that capacitor, means every case in the transient, means if it will be voltage will be initial voltage will be 0 volt, then we can say that that is half CV square, total energy is CV square. Always.
Yes, always in a RC circuit, whatever, how many resistors are there, how many capacitors are there, but the energy lost in the group of resistors is CV square, and the energy stored by the group of capacitors is again CV square, half CV square. Okay. Energy dissipated by the group of resistors is half CV square. Energy stored by the group of capacitors is half CV. Total is CV square.
Okay. And in case of inductor, continuously current is flowing,
to maintain
power is distributed.
Now I will give one important statement. You listen. See, in inductor to maintain energy up to infinity, current also has to go up to infinity.
Yes.
But as current is going up to infinity, losses are infinity. That is why RL circuits are inefficient than RC circuits. That is why in all electronics we take RC circuits. Electrical, electromagnetic energy, bulk energy, but electrostatic energy, small energy in our electronics. See, in all our electronics, sir, RC coupled amplifier, RC phase shift oscillator, multi-vibrators, integrator, differentiator, their capacitor is the winner.
Okay.
As capacitor can handle less energy, but more efficient circuits they are. But bulk energy conversion at power level only inductor can do.
Yes.
But inductor is inefficient when compared to capacitor. That is why electronics is smarter than electrical. We say na. So EC people like RC circuits, electrical people like RL circuits.
RL circuit.
We study at low frequency, they study at high frequency.
And sir, that problem you are completed that I of t greater than 0, that VOC by ISC.
Yeah.
That problem I calculated by taking that voltage source short circuit. That
you can do. Yes. To find resistor alone, I gave the shortcut also. Na, correct.
Okay.
But here I gave why, because I don't want to confuse student. Because it is category 2, I will do like category like that.
Actually, I got wrong answer, so I confused.
No. Actually, in terms of resistance, yes, in terms of resistance, you can do directly also by removing this. Yes or no? Only for resistance, you can also do like that. But my only explanation to student is, if it is both independent, dependent, I teach like my style. Okay, category 2 like style. Okay.
Yes, sir. Sir, that neon lamp problem. Neon lamp problem. That neon having. Can I say that neon having very high in resistance? So that
initially, no. Initially, until it is ignited, it is like open circuit between two electrodes only.
Yes, sir.
Okay, so my expression, though it may not reach finally 100 volts, I know that, because once the lamp get ignites at 75 volts, that voltage will come somewhere between 0 and 100 actually.
Yes.
But here, what is my argument? Though it will not reach 100, until the lamp triggers, this expression is valid. Okay, the more clarity I will give you, that I will write here. This expression is valid. I will write here. This is valid until lamp is triggered. Until lamp triggered. Yes or no? That is why it is no confusion now. No confusion.
Another here same doubt. If it means starting, it will be charging suddenly. Capacitor is charging.
Why we kept actually capacitor? Because actually these neon lamps are very delicate, sir. If you give sudden voltage, the arc rupture will happen and the lamps will burn. See, most of our incandescent bulbs, tungsten filament lamps, and this mercury vapor, sodium vapor, mercury halide lamps, sir, sudden jerk voltage, they will rupture and they will burn.
Okay.
To safeguard that, capacitor we kept. Why capacitor? Because capacitor will not allow sudden change in voltage.
Yes, sir.
Gradually it will ignite. See, you see some old street lights, that yellow color halogen and all this, sir, slowly they will ignite. And even you see in modern cars where halogen lamps are there, they will slowly get brighter, not suddenly brighter.
Okay.
That is why, yes, that is the
yes, sir.
Yeah, sudden change is not allowed here.
Okay. Thank you, sir.
Right. Welcome. Vinita, please, Vinita.
Sir, in the category 4, sir.
Tell me category 4. Tell me what is your doubt. Tell me last doubt. Tell me what is your doubt.
Yes, sir, in the series RLC.
What is your doubt?
Sir, the total voltage response is sum of steady state voltage to steady state current.
Sorry. I wrote wrong. Thank you. Your name is Vinita, na?
Yes, sir.
Thank you. You are correcting me always. Okay. See, steady state voltage plus transient voltage. Actually, voltage only. But why I took voltage is important here. See, in source free, I was very casual. See, in source free, I took current because it is series and equal in all elements. So casually I took. That is why here I use the term called preferable state variable. But here in step response, current if you take, current becomes 0 in final value, na?
Yes, sir.
Because capacitor acts as open circuit. That means the steady state part will be missing.
Yes, sir.
Then I cannot teach student what is called total response. Na? So that is why here dominant state variable is voltage only, because voltage across capacitor can exist.
Yes, sir.
That is why in such cases, select the proper state variable always.
Okay.
Okay,
Sir. Thank you, sir.
Right. Then Bimilen is fine.
Sir, in all these problems that in the step response, that is in the LC circuit, sir.
LC, pure LC tank circuit will come later. Pure LC I did not touch. That is called undamped.
Sir, that second order equation. I am
Second
saying.
order, but it is
Sir,
R is 0, which is called undamped. Such all ideal cases will come only after Laplace, sir. Because what happens now in time domain, if I teach, it will come, but students get confused. Practical cases is pakka, there is a practical register with either inductor or capacitor. So practical possible cases are always either overdamped, critically damped, or underdamped only. But
sir, here is the
pure LC, it isn't. Pure LC, it is called undamped, and if it is native resistance, it is called that is natively damped. That is unstable system.
Okay. But register always we are getting positive, so this will be alpha will be definitely negative.
I will give you tomorrow. Remind me if time permits, or when I teach in doubt session, I will take you such practical problems where native resistance is there and instability also I will teach. But that things are not asked in exam, but they exist.
Sir, solar cell, this will provide negative resistance.
Yes, there it will come. I will teach you. That problems are there in some extreme books I have got, sir. There is a book called Dawser and Koo. In Dawser and Koo, he discussed the stability of networks by taking such of positive feedback networks. And their stability is going in the networks as natively damping. Such original circuits are also there with me. In such circuits, if you connect in laboratory, sir, the circuits will explode. The circuit will burn.
Okay. And yes, sir. And sir, here that V steady state and V transient, always you have to select that proper V value. Means
see,
state,
that is why state variable selection while doing problem is always important, because that will give the correct sense of the answer. If it is step response, even steady state is expected now, so I take. But however, if in exam he is asking whatever he is asking, that you do, not a problem. But for me as a teacher to explain here steady state and also transient state, I cannot take current, because if I take current, steady state does not exist here.
Okay.
So that is why voltage is dominant.
Yes, sir. Some problem it is given dV by dt for 0 plus. Here directly we can equation write and put value.
Yes, we can do that.
Okay. Thank you.
Right. Then now, that is Bimal is fine over. Imtiaz.
Good afternoon, sir.
Tell me, Imtiaz.
Sir, one question is there where we are using that 3i is the dependent source.
Dependent source. Tell me.
Sir, in that we are finding the R equivalent means L will be open circuited, means from that we can find no, sir. Can we take as I equal
category 1? Actually, L will be now that is a mistake. You don't misunderstand. See, it is a resistance seen by the inductor while working. See the term I am using. It is the resistance seen by the inductor while working. Not that I am saying that. Not I am saying that. Array inductor is open, current will not flow. That is not my argument. See, my argument is it is a resistance seen by the inductor while working. That is called effective resistance. Not that if you open, suppose if you open that inductor, current becomes 0. I become 0 means dependent source becomes 0. Short it. Then you may say, sir, 4 in parallel to 2 is not the correct meaning here.
Okay, it means effect resistance we are discussing in the starting.
That is not the meaning. So it is effective resistance is the resistance offered while working.
Yes, sir. Effect resistance.
That is the reason. That is why here we use category 3 by exciting it, not by de-energizing it, because the effect of dependent source also should be taken now.
Yes, sir.
Yes.
Sir, one more, sir. In the find the Vmax in the transformer is there, sir.
Yes. Tell me. I understand.
Sir, in that we are using only L equal to 8 milliamps. Why not we are taking L equivalent means L1 plus L2?
Because however the reason is if you convert even into T equivalent, it doesn't matter. The reason is because see the secondary is not excited and it is open. That is why that effect is not considered. But actually, if you close the secondary and I ask what is the maximum current in the secondary winding, then that concepts will come.
If it's short, then only.
Because electrically that side is open. So electrically this is only RL circuit. First order RL circuit it becomes. And you see, even secondary side closed, such things I will teach you tomorrow in Laplace transform. There you will enjoy even such problems.
Yes, sir. Sir, one point is clarification I want, sir.
Tell me.
After that, we are discussing problem as a 100 U of minus T means whenever you get U of minus T, it's a transient problem, no, sir.
See, 100 U of minus T means 100 volts is becoming 0. Yes, 100 volts becoming 0. Yes, is considered as short circuit. Yes, 100 volts becoming 0 is considered as short circuit.
Yes, sir. First, I think I said whenever I have given a switch, it's a transient problem. After that, I clarify as that U of minus T means at that time it's a transient, no, sir.
Yeah. At the time, it is actually transient, but we are finding solution. 0 plus problems, tomorrow we are going to do that also. Yes, your doubt also that 0 plus such initial condition problems also, tomorrow we are going to start, because in second order solution, there are two constants we need to find now.
Yes, sir.
See, there are two constants. See, in this also A1, A2 I need, A1, A2 I need. So then we will go to initial condition problems, not like first order. In first order, only one initial condition, go to previous state. But here that 0 plus problems are important, which I will start tomorrow morning.
Okay, sir. Sir, one more, sir. In Leon problem.
Ah.
Sir,
Then,
V of infinity is 75, no, sir. I
No,
confused
that is what I am trying to argue. See, that is what I am trying to argue. See, I am first not considering lamp and my expression is valid until the lamp is triggered. So I am assuming that it is reaching 100 volts. I know it will not reach 100 volts. Once the lamp gets ignited, there will be a different voltage that will be dividing across R and the lamp. Yes or no?
Yes, sir.
But my argument is valid until the lamp is triggered. Solution process is correct, but I know this expression is valid only until the lamp is triggered. So until lamp is triggered, why can't I assume 100 and go? But once it is triggering, yes, once it is triggering, it will be a different value.
Yes, I got it.
Yes, because
Sir, one more,
initially
sir.
lamp is open circuit. That is the reason.
Yes, sir. Sir, one more, sir. In
Ah.
the starting, we are discussing as the time constant 36.7% is there, sir.
Time constant of
Time constant of any circuit. We are
it is the time taken. Yeah, tell me, what is your doubt? You tell me.
Sir, in that we are discussing in we study as the settling time. Can we call as a settling time as a 4 time, 4 tick as a
4 time constant is yes, total settling time. Yes.
In control system we study as a settling time. That I'm
settling time. That are more accurate for us. That are more accurate for us graphically. This is my simple definition with observation through the graph.
Yes. Okay, sir.
That
Sir,
is
one more, sir. In category 1, category 2, that graph is coming as the exponential decay, exponential rising, no, sir.
Yes.
Sir, after category 3, we are coming as the underdamped, damp, critically damped.
Yes.
Before category and category 2, can we call as which damp is means underdamped or critically damped for that?
Before coming to category 2, no, that you should say either exponential decay or exponential raise only. It is not cause underdamped or overdamped or nothing. Okay, we should call it as exponential raise or exponential decay, natural response.
We can't say as a damp.
No. We don't use the term. It is exponential raise or exponential decay. That's it.
Okay, sir. Sir, one more, sir. In RLC circuit, the efficiency of RL is the infinite, no, sir. Means
efficiency is zero. Efficiency is zero.
Efficiency zero means it's not useful.
It is not useful in terms of understanding the stored energy in the inductor. That is why in inductors, to maintain energy, continuously losses are taking place. So in inductor, to maintain energy, but what we do in general, our machines, etc., we are calculating only for specific period of operation and calculating efficiency. But if you assume that, suppose in your house, if you assume fan is turned on and going up to infinity, then losses are infinity in the register. So efficiency is zero only, we should say. But what we do, we calculate efficiency for 8 hours, 4 hours. That is fixed amount.
It's a particular time.
That is what we do. Operation cycle we take. But generally in RL circuits, to maintain energy up to infinity, current is also going up to infinity, and resistors create infinite losses. That is the meaning. This is only to argue that RL circuits are inefficient than RC circuits.
Yes. Okay, sir. Sir, one last doubt. In last we are finding as that tau equal to 1 by alpha. Time constant. Sir, before that I thought as the time constant is 1 by omega, means time is 1 by frequency.
No. That here omega does not there, sir. Omega d is there for that too for critically damped state, and that too no. Omega d is there only for underdamped case. That too it is oscillatory, but not envelope. Envelope slope is the decaying function only, e power minus alpha t.
So normally we are telling as that time constant is in proportion to the frequency. No?
That is okay. Time is 1 by frequency. Okay. But that frequency is not the frequency with which the function is behaving. That frequency is only the internal oscillations.
Okay, means it's wrong.
Internal oscillation frequency, not the decaying frequency.
Okay. Yes, sir.
Yes.
That's all. Thank you so much.
Okay. Right. Akshay.
Hello, sir. Sir, that first problem with 20 of minus t problem, no, sir.
Tell me, what is your doubt?
There we had an RL branch and an RC branch, and a short circuit was coming in between them. Then we
Yes,
told that both would act independent of each other.
Yes,
right?
correct.
Sir, like if that resistance was zero, like if both the resistors were not there, even then will that be the same case? Like both would.
Then also same case. But if it is 20 U of t, then that is a beautiful second order, and moreover, a pure LC parallel is a tank circuit, undamped oscillations will come, and such things we are going to do tomorrow after Laplace transform.
Okay, sir. Okay, sir.
Okay. Such all ideal cases we can learn only with Laplace, because in time domain unnecessary confusion, R is 0, formulas will fail. So in all such cases, other than what are standard, we will do with Laplace.
Laplace transform. Okay, sir. Got it, sir. Thank
Okay.
you. Okay, sir.
Yes. So tomorrow, everybody, 7 o'clock, again, we will do our best to complete everything. So happy Diwali, and please come by tomorrow, 7 o'clock.
Hello, sir.
Tell me.
Sir, one last dot in that. Could you open that problem as after the magnetic circuit?
Okay. After that magnetic, you are able to see the screen?
No, sir.
Wait. Now you are able to see the screen?
Yes, sir.
Now which problem you are telling? That magnetic circuit related problem.
Next after.
You tell me that
Problem.
magnetic dot convention
Sir,
problem.
that is 100 U of minus k, 100 U of t, sir.
Coming there.
Next problem.
100 U of t.
Sir, 100 U of t is there, no, sir. Sir, can we find as a normal method before as a DC analysis without using of the transient?
Yes, that is, you can assume switch and assume the same thing. That comes the same meaning. See, 100 U of t, I can write it as 100 volts in series to switch at t equal to 0. Same meaning. Yes or no?
Yes.
Yes, you can do the same meaning is same.
Okay.
Okay.
Thank you, sir.
Okay, right. Ashish Raj.
Hello, sir.
Tell me, Ashish.
Sir, the problem. Yes, sir. The problem just after that category 3, sir.
Tell me.
Sir, here means energy will be stored in that inductor or capacitor.
Yes, energy will be stored depending upon whichever are. Both also can be there. All cases, either inductor only can have initial condition or capacitor, or both also.
No, sir, that question where you told me, sir, that response of the current for IT, where under damped came, sir. Question.
Tell me, what is your doubt?
Just after.
Tell me, what is your doubt here?
So I was asking that this energy stored, sir, means will be in inductor, and how this way means you told us before that it will interchange energies.
See what is really happening here. I will explain you. See this. See in this problem, if I ask these questions like what is, okay, I will ask like this. Okay, I will ask such question because here he is asking current. What is current in the previous steady state? What is current in the final steady state? And who is having energy, either inductor or capacitor or both? You see this. Now this will remove the confusion. Okay. What is the current in the previous steady state? It is absolutely zero now, because when the switch was at A, inductor short, capacitor open na? DC steady state. When switch was at A, what is given? DC steady state, inductor short, capacitor open na? Ashish, you are listening me?
Yes.
When inductor short, capacitor open, what is the current? Zero na?
Yes, sir.
Because capacitor is open circuited.
Yes.
Then at infinity also, see now if infinity when the switch come here, infinity also this resistor will remove the energy and again current becomes zero na? So it starts zero, ends at zero, but don't think transient did not happen. Now here in the previous steady state, now tell me, in the previous steady state, now you tell me, yes, in the previous steady state, you tell me, who is having energy, inductor or capacitor or both?
Inductor, sir.
In the previous steady state, tell me who is having energy, inductor or capacitor or both?
Sir, means that this capacitor, sir. Capacitor.
Yes, capacitor only will have energy. Okay. Now with these fundamentals, see with these fundamentals, I will explain like this. That means in the previous steady state, when the switch was at position A, this capacitor was having energy. Yes or no? That initial voltage came. Yes or no?
Yes, sir. Yes.
Then switch
Yes.
has come here. Now it becomes a source free second order. Now this energy will allow the current to flow in an oscillatory manner, but because it is underdamped, the response will go like this now.
Yes.
That means this current is actually going this way, this way, this way, this way. But in the process, resistor is removing the energy and it is a damped oscillations, damped oscillations.
Okay.
Actually, L and C are exchanging
Yes.
because it is underdamped nature will be like this only. What is the physical meaning? L and C are exchanging energy, but in the process, resistor is also there now. Resistor is also there, which is dissipating energy in the form of heat. And that is how the energy will finally become zero.
Yes, sir.
So current starts at zero, reaches zero, but in a underdamped way. That is the meaning, underdamped way. Understood?
Yes, sir. Thank you.
Okay.
Yes, sir. Thank you, sir.
Okay, right.
Hello, sir.
Yeah, tell me.
Sir, there are some question. Locus, sir. Is it in syllabus or locus? Locus.
Locus, I will teach you in doubt session after 10 days, 15 days doubt session. I will teach you. Actually, after 2007, not even a single question came. But I will teach you after this session, doubt session. You remind me. I will teach you.
Okay, sir.
Okay, never they asked. After 2007, not even a single bit came. So don't worry. Exam point of view, don't worry. Okay. So, but I will teach you in the doubt session after 10 days, 15 days doubt session. That time I will teach. So tomorrow, everybody, 7 o'clock.